Good morning, everybody. I hope you can hear and see me clearly, and I hope you can see the presentation of today. I'm very happy that we have so many registered participants today for our workshop on membrane processes in biorefineries. This workshop is part of the IEA IETS Task 17, and I'm very happy that I can have this day today with you together and my colleague Professor Dr. Michael Harasek from TU Vienna.
Morning.
Before we will start with our keynote presented by Professor Frank Lipnitsky, who is the task leader, I would like to give a few welcome words and a short overview on the task history. So what is our motivation in the IETR Task 17? The main motivation is we would like to strengthen the transfer between research and development related to energy and resource efficient applications and membrane processes in biorefineries. And as part of the national task of Austria, we are embedded in the international framework of Task 17. And our main activities from the Austrian point of view is we organize this workshop of today every 2 years now, and it gets great feedback in the community, so I'm very happy about that. We produce a guideline document on the recent advantages of membrane processes in biorefineries. And we are involved in many networking activities in and beyond the International Task 17 network. And many of the colleagues are today here, so I welcome everybody from the Task network. And thank you for joining in and for your interest. So how did it start? So the membrane process in biorefinery started somewhere in 2014. And the task manager of the current task is Frank Lipnitsky from the Department of Chemical Engineering at Lund University in Sweden. And we have current task members from Austria, Denmark, France, Germany, Italy, Netherlands, Portugal, and Sweden. And historically, I also have to acknowledge my previous colleagues who led the task from AE Intec side and from TU Graz side, which is Dr. Bettina Muster, Dr. Judith Buchmeier, and Dr. Marlene Kienberger. And so I'm very happy that I could take over this already great setup task participation. So just to highlight from the last series what we did so far, we had a very nice task 17 online workshop on September 18th, 2024. And today this is basically the successor of this online workshop. And last time we had around 15 international participants. Today, more than 90 registered. So I'm very happy. We almost doubled the number. That's really great. And we had around 11 expert talks and did 3 workshops. I already mentioned that we are producing a guideline document. This guideline document is available free for download on the IEA Task homepage, but also on the AE Intec homepage, so you can find it there and can download it and have a look at it. And we invite also everybody from today's workshop in contributing, so you can share and provide your research into the document. We will send out some information after the workshop to every participant, and you will get also a template if you like to contribute. So today, as I mentioned, we have 90 registered participants. So there will be 1 keynote speaker, 9 expert talks, and for the first time we also invited PhD students to submit to this format their pitches, and we received around 11 PhD pitches, which is really great. These are very short presentations of only 5 minutes. So I would like to remind all the PhD students to keep really the time limit, otherwise we get into big trouble at the end of the day. So please only keep the time to 5 minutes, and then there will be probably questions, quite some short questions for 1 or 2 minutes. The workshop today overall is about biomass and waste valorization through integrated biorefinery processes. on membrane technologies and resource recovery, and also on membrane materials design and ammonia recovery applications especially. Please also note, everybody, the whole workshop is recorded. All of your presentations are recorded, and we will stream back the workshop at the end of the day, and the link will also be provided and shared on our LinkedIn page, and it will be also forwarded to all the participants. So how do we come through the day today? So in the morning, after this opening, we will have the keynote speaker, Frank Lipnitsky. Then there will be the first task session on integrated process of biomass and waste valorization, and the first pitch session. Then we will have a lunch break from around 12 to 1. And then in the afternoon, it will last until around 5 p.m. with 2 more talk sessions and 2 more PhD pitch sessions. So I wish you and us all a very good workshop day. And I would also like to introduce today our funding agency and Frau Maria Bürgermeister-Mehr from the FFG. She would also like to say a couple of words as a welcome for today's Task 17 workshop. So please, Miss Bürgermeister-Mehr, the floor is yours. You can have a few words.
Thank you. Can you already hear me? Oh, wonderful, because I didn't notice if the microphone is already on. So good morning, everyone. I'm very happy to have the opportunity to participate in this exciting workshop today. This is me and my colleagues at the Austrian Research Promotion Agency. We support the Austrian R&D community and also companies in participating in the activities of the International Energy Agency. This is why is this so? Efficient energy use is a key factor in ensuring economic sovereignty and resilience of our industry and of our country in the whole. So that is why Austria is a member in the IETS technology program and supports there also several tasks, not only this one, within this technology program. So of course it is very exciting for us to learn firsthand what results have already been achieved and also what current challenges are being addressed in these tasks. So I wish us all a very interesting day, and I look very much forward to engaging discussions in this workshop today. Thank you very much.
Yeah, thank you, Ms. Bürgermeister-Mehr. I also have to introduce my colleague, Michael Harasek, and I think he would like to announce the keynote speaker and say also a few words.
Mm-hmm. Yeah, thank you very much, Christoph. A very warm welcome to all of you. Thank you very much, FFG and Maria, to support us over the years. TU Wien is the first time part of this IETS task, and we are very happy to join. Although we had a lot of other activities already and also presented some of our research in the fields of membranes, I believe this is a fast-growing field, and I'm very excited actually also to be part. Thank you very much also AE Intec for the great cooperation and the perfect national lead that you perform over the years. And so without any further ado, and we will meet later on also in a couple of presentations. I would like to announce Frank Lipnitsky, professor at Lund University and the international task leader. A very warm welcome, Frank.
No, thank you very much for the kind introduction. I will share my screen now. 1 second. Should come up now.
Yeah, it works well.
Okay, perfect. Now, first of all, yeah, thank you very much for the kind introduction, and also thank you to Dr. Höfner and Professor Hazarasek for organizing this excellent workshop. This is really a nice opportunity, and it's a pleasure basically to give a little keynote on membrane in biorefineries. And I would like also to extend my thank you to the IETS and to the International Energy Agency and also the Swedish Energy Agency who is supporting this task. Then let us start it. So I would like to talk a little bit about membranes and biorefinery, and I would like to focus a little bit on the research we are doing over the last basically 20 years nearly here at Lund University. And basically how it goes. I would like to start basically giving you a quick introduction to concepts of biorefineries, and then I would really like to look specifically on lignocellulosic biorefineries, basically how to convert pulp mills into biorefineries. And there I would like to look at 3 types of pulp mills and membrane applications there: kraft pulping, thermomechanical pulping, and sulfite pulping. And there will be also a little outlook and some conclusions. So let me start basically by defining actually a biorefinery. Basically, when you look at a biorefinery, you can define it actually in analogy to a petrochemical refinery. So basically, the full utilization of the incoming biomass for the simultaneous production of biofuels, biochemicals, heat and power. And when we looked at the first generation of biorefineries, especially for bioethanol production, there was actually always the questions whether we put more energy in than we get out. And so basically, when we look now at nowadays biorefineries, one of the key point is actually energy efficiency. And for biorefineries, you need high selective, low energy separation technology. And when you look in the literature around, membrane technology has actually the potential to offer this high selective, low energy processes. When it comes to the concept of biorefineries, it is basically depending on the raw materials you are using. Most challenging is it certainly when you start with cellulosic materials, because you often need actually a pre-treatment, for example, steam explosion and others, to open up the structures. It gets a little bit easier when you use starch-based materials. You directly can go into the saccharification step, so basically converting the starch into sugars. Certainly, even easier it gets when you use sugar-based materials, for example, cane or beet sugar. You can directly go into the fermentation, and out you get, in the downstream processing, the fermentation products, and also you get out some byproducts like animal food, solid fuel, heat power, biogas, CO2. One thing which is important to notice, the more we move from cellulosic material to sugar-based materials, the more we have competition actually with our food chain. So basically there's a competition then between producing bio fermentation products from food materials and actually the food we need on our table on a daily basis. So therefore, there's a tendency that we would like to go to cellulosic materials. When it comes actually to membranes in the pulp and paper industry, I mean, actually, there has been actually quite a bit of research in the past. So basically, it started actually in the 1960s. And during this period of time, first trials were done, and surprisingly, actually the first full-scale membrane plant was actually for kraft black liquor in Finland in 1975. And it followed actually by a lot of installation in Europe, North America, and Asia. But then there was also a decline because it was not the big commercial success. But since then, a lot of different type of new applications for the pulp and paper industry have been developed. For example, the treatment of bleaching plant effluents, the concentration of spent sulfite liquor, and the latest development is, for example, the use of man-made bioreactors for the treatment of wastewater from the pulping industry. When it comes to the raw materials we use in lignocellulosic biorefineries, it's basically wood, and wood basically has 3 main components: cellulose, lignin, and hemicellulose. And there are slight variation depending on the wood type, but basically these are the main components. And then you have also some bonus components like hexosan, pentosan, ash, fat, and resin. I stole this nice picture actually from Beauregard, and it shows very, very nicely how you can utilize actually the different raw materials, lignin, cellulose, and hemicellulose sugars to produce actually quite interesting partly innovative products. So, for example, lignin can be used, for example, for vanillin production. Cellulose, certainly, I mean, you can use it for the fiber production. I mean, textile fibers, spur textile fibers, and also for paper production. Hemicellulose is basically, it's probably one of the less utilized raw materials, but you can use it actually for yeast production and bioethanol production. Now I would like to focus a little bit on the research we have done here at Lund University, and I would like to start a little bit with the kraft sulfate pulping. And actually research here started in 2005, and it was actually done by Ola Wallberg, who is now actually the head of the division, and he's heading here at Lund University the biorefinery group, and he actually utilized ultrafiltration membrane to extract lignin from kraft black liquor. This work was then continued basically by Andres Akel, and he looked actually on the membrane filtration and fractionation of biomass compounds, and he basically laid the foundation to implement this type of processes into the pulping industry. And based on, but actually Ola's and Anders' work, they were mainly focusing on ultrafiltration, but there has been a change actually in the pulping industry, or in the industry. Initially, the interest was actually on high molecular weight lignin. And nowadays, there's also quite a big interest in low molecular weight lignins, because they are very good when you want to build up bigger components again with, for example, catalytic reactions. And that was actually the starting point of our last PhD thesis. It's actually nanofiltration of kraft black liquor. In this case, actually, we concentrate the ultrafiltration permeate. And that was by my last PhD student, Mariona Bertanes-Weiss. And basically, when you look at kraft black liquor, it's a side stream of the pulping process, and it contains lignin, hemicellulose, and the cooking chemicals. So basically, the component which disappeared from the original stream is actually the cellulose, which is going to, for example, fiber or paper production. And lignin is a polymer found in many plants and has a potential for many applications. So there's really a huge interest in the industry, both on the high molecular weight lignins and the low molecular weight lignins. And we work, for example, on a project together with a partner, our partner Rainfuel, on actually developing jet fuels from actually lignin. And that is also a project supported by the Energy Agency here in Sweden. Looking at the standard kraft pulping process, basically we have the pulp mill, we get out some paper, and we get out the kraft black liquor. The kraft black liquor is sent to evaporators and then the recovery boiler. In the recovery boiler, we actually recover the chemicals, the cooking chemicals, and recycling them back into the pulp mill. When you want to actually increase the capacity of a pulp mill, often actually the recovery boiler is the bottleneck. So what to do? And one option is basically to integrate membrane filtration. So basically you integrate, for example, ultrafiltration, you actually concentrate up the kraft black liquor, get a lignin concentrate, and you get actually a permeate stream which contains ideally water and salt. The process we looked on is actually this process. Initially, as I said, our research focused actually on the ultrafiltration of the kraft black liquor. So we got out a high molecular weight lignin concentrate. But then we were knowing already at that stage in time, some of the low molecular weight lignins will go through the ultrafiltration membrane into the permeate. So nowadays we're using actually nanofiltration, and we try to concentrate also these low molecular weight lignins that actually at the end of the day, we have really something, a stream. The final permeate stream should contain only water and salts. So how did we start this work on the nanofiltration part? Basically, we were looking for a membrane that has a combination of good lignin retention, especially for the low molecular weight lignin, and a good flux. And this selected membrane should then be chosen to be tested on pilot scale. And also what we did is actually we looked at the economical feasibility of implementing such a nanofiltration step in a pulp mill. And last but not least, we looked a little bit on the optimal cleaning parameters to optimize and maximize the flux recovery. So what we did here in our lab at Lund University, we started actually to select some membranes, and we used actually this small scale membrane rig here, which is actually where you can actually test easily small membrane samples, both polymeric and ceramic. And here we actually went for polymeric membranes, and we tested them in these flat sheet test cells. And then we selected the membrane and went actually to a pulp mill in the north of Sweden, where we actually had a pilot unit where we could put in the membrane in spiral wound configuration and test it. So we tested quite a wide range of commercial available nanofiltration membranes, including also ceramic membranes. But actually, when we looked at the results, actually, the NF membrane from Solcep had the best combination of lignin retention and flux. So actually, we bought a spiral wound membrane for the pilot testing, and we basically had both on lab scale and then pilot scale. We had actually quite good lignin retention of 94 to 98, and also fluxes between 35 and 25 liters per square meter per hour. So we were actually quite happy about this result, and the difference between pilot scale and laboratory scale in flux and retention is partly probably related to the module configuration. So we did the lab scale experiments with a flat sheet cell and the pilot scale experiments with a spiral wound module. Based on these results, actually, we could actually also do a techno-economical analysis. So we looked at the economical feasibility of integrating such a nanofiltration step. And basically, the first scenario we investigated was actually the standard scenario where you have evaporators and recovery boiler. What we get out there, we have no lignin recovery, but we generate actually quite a lot of energy from this process, about 143 megawatt. Then we went for scenario 2, where we actually took out 7 tons of lignin per hour from the process. That has certainly an impact on the power generation. So we ended up with just 126 megawatt power generated. Then scenario 3 was actually, we took out basically most of the lignin we could take out. So basically we had the nanofiltration unit and the ultrafiltration unit integrated, and both the lignins from the ultrafiltration and from the nanofiltration unit were taken out. And in this case, actually, we recovered 10 tons of lignin, and we had a power production of 122 megawatt. And last but not least, we tested actually an interesting scenario. We used ultrafiltration, and we took out from the process 7 tons of lignin from the ultrafiltration step. The concentrate from the nanofiltration step, we actually sent back to the evaporators and recovery boiler. And we found out actually in this case, actually, we could actually generate 129 megawatts. And it was actually quite interesting that actually, because actually the evaporators use less energy than in scenario 2, because we use actually the nanofiltration step as a pre-concentration step before evaporation. So what we found out was actually that the scenario number 4 was, from our point of view, the best scenario. So then we went on and we looked at cleaning. And basically what we know all is actually quite often in industry use standard cleaning processes, typically recommended either by the membrane producer or by the cleaning agent supplier. And our question was actually, is this really the best solution? And we got actually this standard cleaning protocol. We got that the cleaning should be done at 50 degrees C, 60 minutes, and 1 weight% of cleaning agent. And the best question was basically, is this the most effective cleaning, and could this cleaning protocol be optimized? And basically the question was actually, how would such an optimized cleaning protocol that potentially could save energy, cleaning agent, water, and time could look like? And directly, this cleaning protocol certainly should maintain a high recovery flux. So what we did, actually, we did a design of experiments, and we looked at 3 factors with 3 levels. We looked at the temperature, so we increased the temperature from 30 to 50 degrees. We increased the cleaning time from 30 minutes to 60 minutes, and the cleaning agent concentration from 0.05 to 1 weight percent. And the cleaning agent we used was actually a commercial cleaning agent. It was Altacil 110 from Ecolab. And we have selected one response factor, and that was actually the flux recovery. In total, we did 17 experiments, and we used actually the flat sheet membrane. We found best for the process, the one from Novacep, Solcep, sorry. And that's basically the cleaning protocol. Every time we started actually with the conditioning of the membranes, basically removing the preservative chemicals inside the membrane with an alkaline cleaning. Then we measured actually the pure water flux with deionized water. And then we actually fouled the membranes. And I mean, it's important to note, I mean, it took actually 3 days of recirculating the feed until we had a sufficiently fouled membrane. And then after the fouling, we actually measured the pure water flux again. Then we did the cleaning. We used ultraseal at a given temperature, time, and ultraseal concentration. And then last but not least, we measured the pure water flux after cleaning. So we got actually a good feeling from this pure water flux measurement what was actually the reversible flux, reversible fouling part and the irreversible fouling part. The irreversible fouling part was basically related to the pure water flux we directly could achieve after fouling, and the irreversible fouling was actually related to the pure water flux we achieved after cleaning. And these are basically the results of the experiments, the 17 experiments. So we looked actually on the flux recovery, and you can see basically here, without going into too many details, that actually some of the experiments resulted in quite high recovery, flux recovery, and some basically did not succeed so well. The results obtained for flux recovery were then put into a mode, and we set in the mode optimizer, we set actually the setting was actually to maximize the flux recovery without any restrictions. And doing this, basically, the model developed in mode gave us an optimal set of cleaning condition once the optimizer was run. And the optimal set point we obtained was basically a flux recovery of 88.3% when we're using a temperature of 40 degrees C and 60 minutes, and a cleaning agent concentration of 0.8 weight percent. So that was quite good. But I mean, is this really the correct result? Is this result really resulting in a better flux recovery? And therefore, we did one more fouling experiment to validate the optimal cleaning condition given by the model. And actually, when we did this experiment, we obtained actually a flux recovery experimentally of 80.3%. So we were actually quite happy with this, because actually it showed that we actually could improve the cleaning protocol and basically having a quite high flux recovery. So basically, we had certainly a difference between the calculated one and the real one, but it was in the error range of error we could tolerate. But we wanted to also understand a little bit more about the fouling, and so what kind of fouling is removed with the optimal cleaning condition. And therefore, we did SEM and EDS analysis to answer these questions, and 3 membranes were actually examined: conditioned, fouled, and cleaned membranes with the optimal conditions. And here you can see actually the picture, the conditioned membrane, the fouled membrane, and the cleaned membranes. And with a little bit of fantasy, you can see probably that there are slight changes, but they are not so dominant. Basically, the main changes are in this area of the fouled membrane, where we basically have something on the membrane. A little bit more conclusive was actually the EDS, and there we actually saw that actually we have a nice sodium peak on the fouled membrane, and actually this peak was not existing on the Prista membrane, and was also not existing on the cleaned membrane. So our conclusion was actually that sodium was the main fouling component. And basically overall, what our findings were actually with the first part actually of the cleaning and testing, we found an optimal cleaning protocol using design of experiment approach, and the optimal cleaning protocol uses actually a lower temperature and less quantity of cleaning agent than the standard protocol. And we identify actually sodium as a major foulant with EDS. And the Prism and clean membrane have has the same composition, meaning that actually the cleaning removes the sodium effectively. So basically, we did something in the area of saving energy and cleaning agent. And also we removed, most importantly, the fouling efficiently. With this, I would like to move on a little bit into the area of thermomechanical pulping. And there we look especially on the process water. And this is basically based mainly on the work of Johan Tuwander. And basically, this is a traditional concept of a thermomechanical pulp mill. You have the wood, you go into a thermomechanical pulping mill, you add quite a bit of water, 10 to 20 cubic meters of water per ton of pulp. You take out the pulp and you have actually a wastewater you typically send to the wastewater treatment plant. And our idea was actually before sending the wastewater to the wastewater, or the process water to the wastewater treatment plant, we use a membrane and recover some of the hemicellulose. Because hemicellulose is a material which could potentially be used in fermentation processes, but it's also an interesting material, for example, when you want to produce barrier films in the packaging industry. So there's an interest in it, and if you could recover it, it would be great. So basically, we could recover 1 kilogram of hemicellulose per cubic meter of process water. When you produce 1 million tons of pulp per year, you could actually recover something like 20,000 tons of hemicellulose per year. So that would give us some sort of stimulation to look closer into this process. And basically, we looked first on the thermomechanical pulping process water, on the composition. And there we found out actually we have fibers, which are in the sub-micron range. We have extractives, which are probably in the micron range. We have then the hemicellulose, which are in the range of 5-10 kilodaltons. We have lignin, about 1 kilodalton, and we have salts, which are then basically below 500 dalton. So we thought actually that's brilliant, because actually it fits very, very well with membrane processes. Basically, everything which is greater than 0.1 micron could be either removed by coarse filtration or by microfiltration. Hemicellulose and lignin they are basically in the range of ultrafiltration, nanofiltration, and the salts, if one wants to concentrate them up, it could be reverse osmosis. So we did some initial testing, and that's basically the results. And what you can see here very, very nicely, we have the process water. We take the microfiltration. With the microfiltration, we take out the extractives and fines. And then basically we have already quite a clear stream, which we then hand over to the ultrafiltration step. And here we do actually the concentration of the hemicellulose, and out we get actually salts and lignin. And basically this gives you an indication on the purity. So basically we actually achieve a purity of 62% of hemicellulose after ultrafiltration, and that's actually quite an interesting purity already, because actually we tested it actually for packaging barrier films, and it was actually working quite nicely. However, also here we were quite interested in the process, and we wanted to understand a little bit more about the process. For example, do we need actually microfiltration as a pre-treatment? Can we not just do ultrafiltration? And that was actually the first thing we did. We actually did the process water directly on the ultrafiltration membrane, and then we looked at the membrane, and what we saw, basically a dirty membrane. Basically what we concluded there was actually we had membrane fouled by colloidal material, and also that was also evidence in the fluxes we achieved. They were rapidly declining. So we actually went back to the original setup, microfiltration, ultrafiltration. Then again, we looked at the ultrafiltration membrane, tried to get a better understanding. And basically, what we found out that actually the ultrafiltration membrane is now free from colloidal material. So basically, it is a nice, a relatively clean membrane. And with this membrane, actually, we could actually we tested also different types of microfiltration pretreatments to get a better understanding about the process. So we actually started with a very tight microfiltration membrane, an 0.04 microfiltration membrane. And basically, we had a nice flux recovery, and the flux was nicely declining, basically with the volume reduction. We tested then an 0.1 micron membrane, and basically the line of volume reduction was the same. And then we tested also an 0.5 micron membrane. And there we saw actually that the flux actually was significantly lower. And we were wondering, because certainly, I mean, normally you would expect the more open the membrane, the higher the flux. However, this was basically related to the fact that actually the colloidal extractives we had in the feed stream were in the range of 0.2 micron. So basically what we saw here was actually the microfiltration membrane was basically spontaneously fouled by the colloidal extractives, and therefore we had a significantly lower flux for the more open membrane than for the tighter membrane. Our conclusion was actually for this application, probably the best compromise is actually the 0.1 micron membrane, and with this membrane we went actually forward. And the nice thing is actually we had the opportunity to go actually on pilot scale at a pulp mill in the north of Sweden. So we installed actually a process there consisting of a pre-filter, microfiltration, and ultrafiltration. And for the microfiltration, we had actually a nice pilot scale unit from Ligtech, a Danish company, where we use actually a ceramic tubular membrane and a membrane area of 0.6 square meters. And then we had actually, as the second part of the process, we had actually a polymeric spiral wound module with a regenerated cellulose acetate membrane from Alfa Laval and a membrane area of 16 square meters. The picture is actually the full-scale pilot we use, but actually we use this pilot just with one spiral wound element because we didn't have insufficient feed stream. However, what we achieved was basically we achieved also with this process a very nice volume reduction, and also we saw also that the flux was decreasing, yeah, not surprisingly, with basically increasing volume reduction, and we achieved also nice hemicellulose concentrations of up to 32 grams per liter. We did also a little cost estimation here, and basically we looked at the microfiltration part and the ultrafiltration part, and we calculated cost per ton of hemicellulose of about 1,160 euros per ton. And this is certainly an interesting price, but actually there are some additional costs one should consider, because actually there will be potential savings in the reduced wastewater treatment, and that's accumulates to about 280 euros per ton of hemicellulose. That's a positive effect. And the membrane retentate, which is with concentrated extractives and fines, it could actually be utilized another way. It could be actually to send also to chemical recovery, so it could be actually burned basically for energy production. So that actually gives additional benefits, and therefore it could be actually quite an interesting process. Overall, the key findings were actually microfiltration before ultrafiltration is important to remove fouling substances, especially the colloidal extractives. And when you do this, actually you maintain a very, very nice filtration performance, and also you increase the flux during the hemicellulose recovery by ultrafiltration. And we came up with a cost of about 1,160 euros per ton of hemicellulose, which can be improved considering also other savings which are done by the process, less wastewater treatment, and also extractive separation, which can be then sent to the recovery boiler. And with this, I come basically to the last section, basically sulfide pulping. And I would like to look specifically here on bleaching plant effluent And this is actually based on the work by Gregor Rudolf Schöpping. I mean, when you look at sulfide pulping, I mean, and I will not talk too much about it, but I want to mention it at least. I mean, the main application in sulfide pulping is actually the separation and purification of lignin sulfonate. Basically, it's done it's an industrial application, and it's done on large scale. And that's basically a typical product. So you take the spent sulfide liquor, use an ultrafiltration process. In this case, for example, with plate and frame models, but also tubular models are used in the industry. And you use typically some sort of PVDF type of membrane. And what you achieve is basically you have a permeate stream, which contains mainly water and some of the low molecular weight lignin sulfonate, and then you achieve as a concentrated lignin sulfonate stream. So that's actually one of the main applications which is established widely in the industry. But there's another application, and I would like to focus on that one a little bit more. It's actually the bleaching plant effluent. And basically the application is here is COD reduction in bleaching plant effluent in a sulfide mill. And this is actually a case based on a pulp mill, which is relatively close to home. Basically, it's the Stora Enso pulp mill in Nymölla. And they have actually installed a bleaching plant treatment based on membranes. And basically, they have two lines. And they treat, if every day they treat actually, every hour they treat 400 cubic meters of bleaching plant effluent with a COD of 14 to 60 milligrams per liter and suspended solids between 30 and 125 milligrams per liter. I mean, the fascinating thing about this process is actually what they achieve. Basically, they go in with a feed of 400 cubic meters per hour. The permit is 392 cubic meters, and a concentrate stream, which contains most of the COD, is actually just 8 cubic meters. So you actually receive a volume reduction or volume concentration factor of 50. They have two lines. It's a softwood line and a hardwood line. And it's, to my knowledge, still actually the biggest tubular membrane plant in the world. What we did actually for this pulp mill, we looked actually a little bit on fouling behavior on their membranes. And basically, here you see line scans, EDS, and also the cross-section of the fouled membrane. And you see actually there's a fouling layer on top of the membrane. And what we can see is actually one of the things we can see very clearly is actually there's a magnesium peak in the fouling layer of this membrane. So we were quite surprised about this, that it was magnesium. But yeah, we got this initial indication. And we did some further analysis. So basically, we did EDS spectra and SEM scanning of a new membrane and of a used membrane. And basically, comparing the results basically showed us very clearly there's magnesium is the main fouling component. You can see it here very, very nicely. Basically, the top picture, the new membrane, it's very nice and clean. I personally, I think actually the second picture is nicer, but actually you see actually the problem, a fouling layer based on magnesium. And what we did then actually, we wanted to get some feeling on how can we remove this fouling, and we use actually, we soak the membranes in alkaline cleaning agent Brandmark Ultra 17 for 1 hour. And after 1 hour, basically what we saw, nothing happened. However, then we actually put the membranes for 20 hours in the same cleaning agent, and suddenly we had actually a relatively clean membrane. Actually, the magnesium peak disappeared. So basically, it shows also that the length of cleaning is an important factor, not only the cleaning agent. And basically, the key finding from this study was actually that SEM and EDS can help to understand membrane fouling regarding structure and composition, and that the contact time of the cleaning chemicals has an important impact of membrane performance. We would like to move further on with the studies of membrane fouling cleaning. So one of the next steps we did actually already is actually we used nanotomography. And in this case, basically, we had to cut out little pieces of membrane and put these little pieces of membrane, 20 micron in size, on pins. And then we sent these pins actually initially to the Paul Scherrer Institute in Switzerland. And they did actually an initial scan of the membranes, how they look like. And this is basically the first result we got back. So that was actually the membranes, the scan, the three-dimensional scan of the membranes. And you see it works. And basically, based on one scan we did, actually, we demonstrated that it was actually possible to use nanotomography at a synchrotron for actually studying membrane fouling and cleaning. And we did actually more experiments. For example, here's an example from a microfiltration membrane, where we have the pristine membrane, the fouled membrane, and the cleaned membrane. And we can nicely see that actually in the pristine membrane, we have pores. In the fouled membrane, the pores are gone, and in the cleaned membrane, the pores are suddenly reappearing. So we can actually prove that something is happening there. We would like to combine this also with a chemical analysis to get a further understanding. Also, we would like to understand, for example, how deep certain foulings are penetrating the membrane structure. So that's basically ongoing work which we would like to do. And with this, I come basically to the end of my talk. So basically what I wanted to show to you is actually lignocellulosic biorefineries can use sustainable non-food raw materials. So there is no competition with our food chains. So basically wood-based materials could be a good alternative, but there's also straw and other materials. And in this concept, basically membrane processes have a great potential. I focus here mainly on the pressure-driven membrane processes, but certainly also other membrane processes can have an opportunity in the process setup. For example, I would say it could be interesting, for example, to look at membrane distillation or electrodialysis, how they could be integrated in such processes. And certainly cleaning of the membranes can be optimized with the help of different analytical methods. I mean, as we showed, basically SEM, EDS are certainly nice methods, but we use also BET, for example, QCMD in other studies. And basically the key to success is basically the optimization and integration of membrane processes. Certainly, I mean, I did not do this work alone. As I mentioned, my PhD students were involved in the membrane group, and I would like also to thank our sponsors. It was already mentioned, this work is related to the Annex, membranes in membrane process in biorefineries. And last but not least, I would like to thank you for your attention, and I'm looking forward to your question. Otherwise, when you have questions later on, please do not hesitate to drop me a line. Thank you.
Thank you very much, Frank Lidnicki, for this exciting overview and also actually the future of the application of pressure-driven membrane processes in the pulp and paper industries. I think there is time for some questions, and so I would like to ask the audience to raise some questions. I think there's somebody it's already raised his hand. Henrik Lassen, please go ahead.
No, if it's me, Henrik Larsen, you're thinking about. I think I pressed the wrong button, but now I'm here. Hi, Frank. I would like to ask you if you were looking forward to see a spiral element which can have a, let's say, which is more optimized to microfiltration as elements which can also deal with some particles.
I think it would be definitely an interesting aspect. I mean, there has been approaches to use actually spiral wound modules with larger channels in the past, but they have basically disappeared again from the market. So I think it would be very interesting to see actually more open channeled spiral wound modules for microfiltration.
Yeah. Okay. Thank you.
Mm-hmm. We have a second question from Oskar Schmidt.
Yes, thank you. So Frank, always nice to hear your presentations, and we follow, Ecoelix is following your work closely, so we always think that you work with interesting stuff. I just had a question regarding the selection of membranes, since I guess that is what I've been messing around with the most, let's say, and especially how it fits into temperature profiles for different streams. That is what I see is the most kind of I would say complicated from a process economical perspective then, and especially in the craft liquor filtration section, because I saw that you used polymeric membranes for that process. That means that you need to take it down, the temperature down quite substantially, I guess. And don't you see that will affect the performance and the selectivity as well, have a quite high impact on that?
I mean, certainly. I mean, it has on the performance definitely an impact, because basically the flux is proportional to the temperature. So there's a relationship. So at higher temperatures, I get basically higher fluxes. And then also basically you have an impact then also on the selectivity. So, I mean, we would ideally go to higher temperature. And we had actually tested also ceramic membranes for nanofiltration at that stage in time from 2 different suppliers, and they were not as good. Even though they could run at higher temperature, they were not so good in the performance as the polymeric membranes. Actually, I should say that we are certainly open to ceramic membranes, especially for their high temperature capabilities, because actually the initial part, the ultrafiltration part, we actually run with ceramic membranes.
Okay, that makes sense. Because we have seen, as you know, we have done a lot of work on same kind of streams that you have done here, and I see very interesting behaviors. Let's say over 100 degrees. Let's say when you go, it's interesting. Let's say it's a challenging, but especially when it comes to selectivity of the membrane,
I mean, we would like to dig actually deeper into it, because we have actually just maybe that might be also an area for collaboration. Is actually we have a pilot unit here which can run 160 degree at 16 bar.
Yeah.
So that it's something we would like to at some stage actually try to out. And also one should keep in mind. Polymeric membranes, polysulfone, polyether sulfur membranes, you pay for a little bit with the membrane life cycle, certainly, but they can actually go to 80, 90 degrees also.
Yeah, exactly. But exactly. I've seen that, and they tend to become a little bit more open at that point at higher temperatures. No, but I think that I will discuss with my colleagues, and we can maybe find some projects together, because I think it's really interesting work that you do. Thank you.
Thank you.
Yeah. Thank you very much for this interesting question and great answers. Are there any further questions? Maybe I have a question, Frank. I think you also did techno-economics of your processes, and I believe congratulations also to contribution of this Guinness the Book of World Records, actually with this largest application of membranes in the pulp and paper industry. Now, looking at energy consumption somehow, where do you see the largest trade-offs and the largest winnings of membrane processes in the pulp and paper industry, really to save energy?
I mean, we see it. I mean, basically we can save energy because we can reduce the size of evaporators in the pulp and paper industry. So there I see actually the major opportunity. And the other thing is actually one important thing is actually most of the membrane process, or this pressure-driven membrane process where I focused on, basically they're using electricity. So electricity is basically an energy which has a high potential to be actually coming from sustainable sources like wind and solar. And so that's actually quite interesting. So we actually drive the electrification aspects of the industry very nicely when we implement membrane processes. And I think there are even more options also to save energy, for example, by installing, for example, or to consider at least, for example, the use of membrane distillation. Membrane distillation needs a lot of low-grade heat, but actually it utilizes the heat very efficiently. So that could be something interesting probably to investigate a little bit further.
Yeah, thank you very much. Once again, any further questions? I think if it's not the case, Christoph, I hand over to you now.
Yeah, thank you, Frank, for this very nice keynote and all the audience for the questions. We will go into 10 minutes technical break and then come back at 9:10 with the first session on integrated processes for biomass and waste valorization. Okay, I think we can start with the first talk session of today, and it's a great honor to introduce my colleague, Dr. Michael Harasek from the Separations Engineering and Biorefinery Technology, Institute of Chemical, Environmental and Bioscience Engineering from TU Vienna. Michael, we are very much looking forward to your talk.
Yeah, thank you very much, Christoph, for your very kind introduction, and it's a great honor for me to speak today to this distinguished audience on with all the membrane experts here. And I think you can see my screen. Yep. Okay. So my talk will be about system design and integration as a success factor for large-scale membrane biorefinery applications. I think that is sometimes, it's a topic that is sometimes actually underlighted because we as researchers, mostly we try to actually test the membrane at lab scale. Maybe we try to see and look at fouling, but then it kind of stops. So I'd like to highlight this topic a little bit in my talk. Just reviewing why system design matters, I think it's important actually also in relation to bringing separation technologies into biorefinery applications, that there is an energy and cost dominance. So that means with increasing specific costs for energy, the OPEX are really important, but at the same time also reducing the CAPEX is another aspect. So therefore, actually having a proper system design can definitely contribute to prevent late-stage expensive retrofits of plants. Very important. Another important aspect is the purity, which defines the value. So as such, a multi-staging of a membrane process or a combination or hybrid processes actually are required to receive the product specifications, whatever the product is in a biorefinery context. Furthermore, also, of course, considering the energy and cost aspects here, sustainability is also important. Heat integration, solvent loops, exchanging solvents, reducing the amount of solvents, the amount of water that is in the circle. Actually also is an important aspect where system design for sure matters and contributes. And further also, it's important actually to develop resilient systems. And when we talk about resilient systems, we want to actually tackle feedstock variability. Because of biomass heterogeneity, about variations over the year, but also having a multi-purpose plant so that they actually can treat different feedstocks. This is actually something that is important as well. And also the aspect of course, what I wanted to also address and highlight here is to develop robust control strategies of such implementations, also to increase the tolerance for fouling and composition shifts. Membrane processes, that's what we talk today about, is actually, they indeed offer quite a strategic importance. This is because membrane processes do have a key strength, a couple of key strengths. It was already addressed by Frank earlier and earlier today. But important for us is in particular the low energy demand that we see compared also to thermal process in particular. So when we replace processes, but also when we replace other separation processes, energy demand can be an issue, and I will have two two examples where we can address this aspect here too. The selectivity, in particular, which is excellent, in particular for a couple of molecules, macromolecules, ions, water, solvents. Very good to implement membranes. The mild temperatures, which is also important for heat-sensitive bioproducts, in particular for high-value biorefinery concepts where the bioactives are target, and the scalability modularity. So that means sizing according to the process needs is something that definitely is a big advantage of membranes, and of course also shifting a batch process or a fed batch process with a lot of storage in between into a kind of continuous processing that is definitely also a high potential where membranes may play an important role. Now, the typical applications of membrane process application in biorefineries was already mentioned. Of course, biomass pretreatment, upstream side, downstream side, solid liquid separations, purifications of values of value compounds such as sugars or organic acids, polyphenols, proteins, amino acids, etc. Recovery fermentation broths, where we have biofeedstocks, removal of inhibitors, an interesting topic as well. Water recycling, water has a strong dominance in biorefinery process. It's the core solvent that we have, and effluent polishing. There was just this very nice example before. And also, of course, dehydration. And here we have very nice technologies such as pervaporation or vapor permeations actually can contribute to the removal of water, for instance, for ethanol, bioethanol, etc., by membranes. And further on, also considering biogas biorefineries, and I will highlight this topic a little later. Is actually to consider biomethane as an interesting product from biogas, and here membrane is the dominant technology to date. As such, I consider membrane operations really as a key contribution in that field. On the right side, you just see one of our projects that we did in the past, where this combining of different membrane processes in a so-called green biorefinery concept, which was presented some time earlier already, where you see that a silage juice, a pressed juice that contains lactic acid, that contains amino acids as value products, but highly contaminated actually with a set of ultrafiltration, nanofiltration, ion exchange polishing, concentration by RO, also bringing in electrodialysis to separate for separations, is actually a concept which was piloted. I mean, it's expensive, of course, because of those many different technologies, but it shows also and highlights also the potential of membrane applications in that field. Let's quickly move, as time is short, actually to two examples that we worked on in the last, I would say, 15 plus years. And one is the sugar beet biorefinery. And here I want to emphasize also what is the core task of this IETS Task 17 is to look at energy savings. And actually here we looked at nanofiltration and RO for replacing evaporation technologies. And if you look into the classical treatment of sugar beets to receive saccharose as a product, starting with mechanical processing, milling, cleaning, then clarification of the juice after the extraction under heat, decolorization technologies, removal of solids again are the classical way towards the product. And then there is a clarified juice at some point, and that actually requires to be crystallized. But prior to that, it's usually concentrated by evaporation. And looking into membranes, we have a couple of possibilities here. We could actually apply MFUF at an early stage, but also considering that it's all processes are there very prone to fouling. So as such, our focus when we went into that topic was really to do the concentration, because here's the highest savings actually, because the most energy demanding process is the evaporative water removal prior to crystallization, and also the evaporation crystallization that we have here. So we ended up with a couple of ideas to do that, looking into that and said, okay, well, can we actually replace the multi-effect evaporation in some way or other? And here the idea was, if you look at that, to concentrate the thin sugar juice, which is much less prone to fouling. And just by this simple balance here, you can see that starting with 100 tons per hour in a typical sugar biorefinery with thin sugar juice with 15 tons of sugar and 85 tons of water per hour, a membrane could actually remove 70 tons of water, and then having a preheater of the juice and bringing this to the evaporator. So this potential of removing quite a big share is quite exciting. And now rolling this out to the world sugar consumption of 180 million tons, that was the statistics of 2020, is quite also an interesting aspect here. However, looking at the thin sugar juice and also its concentrates, we actually face a couple of problems. And one is the osmotic pressure. As you see here, usually sugar in the sugar industry, we call the sugar concentrations is computed as bricks. So that's gram sugar per 100 gram solution as a percentage. What you see here, that the osmotic pressure really explodes. And if you consider that crystallization happens at 65 to 70%, or degree bricks, the osmotic pressure is far too high actually to achieve such concentrations. Even 50 bricks is quite demanding. And furthermore, also we have the viscosity aspect here. And these are the green lines. We have severe viscosity at high concentrations, as you can see. So it's like really a honey type of product. And so also this has to cope with. So we thought, okay, how can we tackle this? Considering the osmotic pressure, we said, okay, an RO can only go to a certain concentration even if you're operated at 60 bars or 70 bars or high pressure RO. Usually going beyond 30 bricks is not possible. So we said, okay, well, why not use nanofiltration as the second and third stage in a multiple stage design? And with this, the nanofiltration has actually a controlled leakage of saccharose. If we use loose nanofiltration membranes, so saccharose is partially permeated and only slightly concentrated. So as such, the osmotic pressure difference between the permeate and the feed side can always be controlled, is in the right range. And then that could be extended further, just considering viscosity aspects, temperature aspects as well. And so actually we went up with a pilot, we went up with a patent, and we integrated this also here in our labs in a pilot that you can see here, where we have a single stage RO, a single module RO with a 4-inch cartridge module here. And then for the feeding back, actually, we have also mixing tanks involved, and we have 2 nanofiltrations modules in parallel in the second stage, and 2 loose nanofiltration modules in the third stage. Altogether, we ended up with quite some nice findings of this pilot plant operation. So if you go and consider the 3-stage process, actually, we have the feed pumps, which bring the high pressure. So usually we operate at 32 bars. It's not so high, but still requires some energy consumption here. And we have to boost. So we have the boosting pumps of RO and both of DNFs, and actually to receive sufficient cross flows. And with this, actually, we can reach around a specific energy consumption per cubic meter of thin juice is 3.6 kilowatt hours, but the water removal, which is actually more relevant, is around 10, so 9.85 kilowatt hours per cubic meter of water removed. If you compare this with a single stage RO, of course, we cannot concentrate so far. So actually the specific energy consumption per cubic meter of feed, so thin juice, is less, is half like that. But the specific energy consumption is higher. So with this process idea, we can actually target a lower energy consumption. So as you see also here in an energy balance, the major contribution in the sugar beet factory, in the sugar beet refinery is really the evaporation, the crystallization. Other energy consumers are the extraction and also purification. So here we can actually target the savings in 2 phases. One is the concentration, the evaporation, and the second is also reduced energy demand in clarified thin juice preheating. So we don't have to preheat everything to 130, 140 degrees, but just that what is actually the concentrate of the membrane process. So this is like the first example in this short presentation here, and I'm very happy actually that we piloted this also in a sugar factory here in Austria, and ran such a process in a side stream. Also very happy actually in the cooperation then. We worked together also with Frank and Alpha Laval. So very, very nice contributions. Quite some old thing, but still a nice idea, and it's could actually be rolled out also for other syn juice concentration technologies. We did it for fruit juice and other technologies. Bringing also system design aspects now to a different topic, which is not so much highlighted also in the IETS task so far, but we worked a lot on that, and that is biomethane from biogas. Biogas biorefineries are really a lot. We have in Austria just in Austria like more than 300 biogas plants to produce biogas, to produce electricity, or actually also to upgrade the gas. So as membranologists, of course, it's our pleasure to consider membrane separations here. And here we have usually polymer membranes that do the job. And here the target is in biogas, which is a mix of methane, CO2, it's saturated with water. We have H2S, we have ammonia, we have a couple of other contaminations, also maybe some air components, oxygen, nitrogen, even in the gas. And we have quite some materials that are commercial, and that is polyimide-based membranes with high selectivities that actually can separate the CO2 and the water in a gas permeation process. So usually bringing the biogas to pressures of up to 50 bars, and then bringing this compressed gas after pretreatment, maybe after desulfurization, to the membrane. And of course, the selection of a proper membrane is quite interesting. And as you may know, in gas permeation, we usually use the so-called Robson plots. It's quality over quantity. So you see the alpha, the ideal selectivity ratio of permeability on the y-axis, and the permeability on the x-axis. So we have membrane materials that have a high permeability for CO2, but are less selective, or we have highly selective materials, but with less permeability. So it's always a trade-off here, also that we see here. So back then, that is more than 20 years ago, we said, okay, well, let's consider a two-stage separation process in the first place. And as you may know, in distillation, in countercurrent distillation, rectification, we also use so-called cascading. So we have multiple stages with backflows of liquids and gases, and we can use actually the same concept and apply this to membranes. So as you can see here, if you just look into the simple design with two stages, here we bring in, after some pretreatment, removal of ammonia, removal of H2S, etc., we bring the gas actually to the first membrane stage. Biogas is usually 50 to 60% methane. The rest is mostly CO2. So in the first step, we actually remove CO2, so we get an off gas here. But we do not enrich to the desired grid injection concentration, which is 98%. So we end up with maybe 80%, 70%, and then we bring the gas actually to the second stage, where we enrich to the final concentration. However, the permeates of the second stage is too methane rich, so we have to bring it back. We feed it back to the section of the compressor, and so with this looping back, actually we can improve our energy consumption, but also reduce our losses. So this is something that is really important when we design such technology. So after some tests, we had projects at a small plant with a mini pilot. We were quite happy actually to have our first project that was real world. We did this south of Vienna at a quite big biogas plant, but only with a bypass stream in the first place. So our bypass stream was like 180 cubic meters of biogas, which is around 100 cubic meters of biomethane, and that is around 1.1 megawatt of thermal energy. So 1.1 megawatt to the gas grid. Now we know with our natural gas imports, this is really a severe topic actually also in this regard. Now to bring in and substitute natural gas here. But I want to bring to your attention that when you see this plant, as we implemented this with a two-stage piston compressor on the right side, and with these membrane modules here, that we have an inverse design. So that means the first stage is actually smaller, which harvests actually the CO2 that can be emitted with a small concentration of methane only. And the second stage, which is the cleanup stage, is really large. So that means here we have a membrane area ratio of 4:1 or 3:1 between the first stage and the second stage to first stage. So this was really the key success actually to reach grid injection properties. So that was 98%. So all in all, we had to integrate this. So we had the biogas production plant there. There was an existing biological desulfurization, which we actually substituted later on by chemical oxidative scrubber. Most of the gas actually goes to CHP, but the share actually we take, bring it to the compressor, bring it to the dryer, and then to the two-stage gas permeation, with a recycle to the compressor and with a recycle of the off gas to the CHP. So as such, it's a zero emission. It's a zero methane emission implementation. That was our first step actually, and with this we achieved the quality. We had pipeline, we had odorization, we have high pressure compression. So it's really a nice demo project that we did then. Also highlighting this aspect of process design, and with this graph here, you can see that. There is a trade-off between methane recovery and energy consumption. And the question is, what is feasible with this two-stage design? And we said, okay, well, depending on the membrane selectivity for the CO2 methane separation, we can find biomethane recoveries of 95-98%, probably feasible. When we go beyond this 0.4 kilowatt hours per cubic meter of specific compression energy of the feed, then we are quite off already. So this is, I think, something that's very important. We can also play ground, and we do that now, that we establish different membranes in the first and second stage with different selectivities. So it's really quite a big playground, and we have a couple of publications on that. But further also, we said, okay, well, 2 stages is probably not enough. So we went into a 4-stage design. It's also patented. And we investigated a variety of different process designs with 1 compressor, with 2 compressors, with 3 compressors, with 4 compressors. What is the best way on how to do that? And what we see is this simple cascading. So that means actually we try to reduce membrane area and energy consumption with less recycle in the first stage. First 2 stages, and then we actually take the permeate and recompress that in a second 2-stage downstream cascade design, which we also patented actually, and it is quite feasible, and that actually went also into an implementation. So this first pilot that you saw was now fully implemented. That's already a couple of years ago, and we celebrated more than 10 years full-scale operation. So all the biogas, which is around 1,000 cubic meters per hour, so it's around 6.5 megawatts thermal, is now upgraded in this plant. So that's a 2-strain plant with two lines, 4 compressors, and 4 stages. And with this, actually, we can reduce our energy consumption to less than 0.2 kilowatt hours per standard cubic meter of biogas, considering that the biogas contains around 6.5 kilowatt hours. So the energy consumption is really in the low percent range, and that was quite successful. And there are a couple of plants out that actually use the same concept, this 4-stage concept, and with really very low energy demand. And good control. So here you can see some of those equipment pieces. We looked into desulfurization. It's not enough time today to speak about that, but that is also important because we have fluctuating inputs from the biogas digester with regard to H2S concentration, so that also has to be met. And we have quite a successful implementation here. Actually moving from biological desulfurization to a chemical desulfurization. With this, I'd like to summarize shortly. system design and appropriate integration of membrane process steps is for sure a key success factor. We believe that there should be also more focus on multi-staging. Even with, let's say, low selective membranes, there can be a lot of achievements and improved product quality with the proper staging. I think that inverse cascading, I showed this both in the gas separation, but also in the NFN, RO-NFNF idea. Is something that is interesting and that it should be more considered, and such contributions can actually reduce the energy consumption. All kinds of biorefinery processes, also replacing conventional technologies, for instance, in the biogas upgrading, like water scrubbing, PSA, amine, and beyond. And with this, I'm finishing, and I'm happy to answer any questions.
Thank you, Michael, for this very interesting talk. Two things I noted down myself. The one is purity defines value. I really like that statement you made in the beginning. And the second one I think is really interesting, is that the multi-stage application of membranes really shows very great possibilities. And I think especially in this round, this is a really good boost of thinking a little bit more in combining these processes. So thank you a lot. Do we have some comments from the audience? Some questions to Michael? If he answered all the questions to you with his talk, I would directly move on to our next speaker, which is Lidietta Giorno from the Institute of Membrane Technology, Enrico Trioli in Italy. Lidietta, I'm very happy that you participate again in our workshop concept, and I would directly ask you to take over and start. I think you might still be muted.
Okay, can you hear me?
Yes. Perfect.
And you can see the presentation as well.
Yes, everything works.
Okay, thank you. Thank you very much, and good morning to everybody. Thank you again for giving me the opportunity to discuss of these nice topics with such an impressive audience. Very interesting presentations from Frank and from the colleague. I will a little bit move now to a focus on a more, let's say, detail about the membrane process, and especially the bioreactors and the biocatalytic membrane reactors to valorize biomass compounds. And I will focus on what are the potentialities and what are the challenges, okay? Because we have very important opportunities with these systems, but also we have to face a few challenges. First of all, I would like to start with just reminding that when we discuss about membrane bioreactors, we have two major roles of the membrane. In one case, the membrane serves as a separation unit, and we may have the biocatalyst, which is recycled along the membrane circuit, or which is blocked at the membrane module. And we can have a side stream configuration or a submerged configuration for all the cases I'm going to describe. In the other case, we have membranes that serve as both the catalytic site and the separation unit. In this case, we specifically call the membrane biocatalytic, meaning that the catalyst is at the membrane level. And then we can have the catalysis on the membrane because we mobilize a biocatalyst on the membrane. And here are depicted a number of different configurations. I will go through the various types. Now, for the first configuration, where the membrane serves as a separation unit, we have mainly cells and some enzyme as well. The reason is that enzymes are quite labile molecules, macromolecules, and during the recycle they can be deactivated. While in the case where the catalyst is on the membrane, is at the membrane level, we can have that the biocatalyst is mainly enzymes and rarely cells, because cells, like bacteria, they perform their reactions while they grow. And if they grow in a membrane, of course, they will pack the membrane. But there are cases where we can use bacteria in the just vegetative phase. We just use their enzymatic tools. And therefore, some example of cells attached to the membrane is also present. I will initiate with the biocatalytic membranes and highlighting the advantages and well-known disadvantages. Of course, we have that enzymes are extremely highly selective. They have no or very low intermediates or byproducts, which means that the solution is already quite purified, and we need less downstream processing. And also they operate in mild conditions, nearly to room temperature and atmospheric pressure, which means low energy consumption. However, they have low mechanical stability and low chemical resistance, and they are expensive molecules so far. Therefore, what we try to do is to immobilize enzymes, and what literature tells us is the general behavior that free enzymes lose their activity very quickly, while the immobilized enzyme reduce their initial activity, but then are stable as a function of time, much more stable. So the advantages of immobilizing an enzyme and having a biocatalytic membrane is then that the catalytic stability is enhanced, the selectivity is maintained quite well. We can decouple reaction rate from residence time. If we think of a stirred tank reactor, the residence time is just the time that the whole reagent is converted, while with the enzyme within the membrane, we can go more close to the molecular level, let's say, or microscale level. Therefore, we can have a residence time which is decoupled from the overall time we need to complete the full conversion of our reagent. The disadvantage is that we need to immobilize the enzyme on the membrane, which are procedures that, of course, require additional work, additional materials. Once the enzyme is deactivated, if we are not able to remove the enzyme easily, then we have to waste both enzyme and support. Therefore, new strategies are more focused on the way of immobilizing enzyme in an easy way, and then easy way to remove it while preserving the support. Reactions may be are limited by mass transfer, because when they are in the membrane, we have to balance the reaction rate with the mass transfer rate, and we can work at the maximum activity of the system when we work in reaction limited conditions. We have a low degree of freedom in controlling transport and reaction conditions independently, because they occur in the same environment, in the same reactor. Just to underline the problem of the mass transfer, we have to recall that an enzyme reaction is given by the combination of an enzyme with the reagent. Then we have an activated complex, which is released into the enzyme plus the product. When we have the enzyme within a membrane, we need to have an additional time of transport of the reagent to the enzyme, and then of the release of the product from the reaction site to the bulk where we can take measurements. And therefore, there is an initial delay in the observed activity on the observed reaction rate. What are the type of enzymes that are commonly used in biorefinery? Have been in the previous lectures, Frank has nominated some of them, but here is the spectrum of the most used ones. to this end, maybe one of the research topics that needs to be more developed is to derive enzymes from more resistant sources, so from extremophilous microorganisms, because they are macromolecules that are more stable in diverse conditions. I will start with a case study, which is the production of L-malic acid, which is used as a food preservative. And this was obtained by the conversion of fumaric acid into the L-malic acid by a fumarase. Here there is some mismatch with the equation, but anyway, what I want to highlight here is that the size of the reagent, as you can see, is very similar to the size of the product. So one of the advantages of membrane bioreactors and biocatalytic membrane reactors is that if we can separate the reagent from the product, and the membrane is selective and allows the passage of the product alone, then we can reach full conversion, because based on the Le Chatelier principle, if we remove the product, we shift the reaction towards the right, towards the formation of the product. But when the two molecules are very similar, a membrane is very difficult to distinguish with this. So what we can do is to use the membrane as a reactor, in such a way that we can tune the residence time and to reach the highest conversion rate, but we cannot shift the equilibrium reaction. So here is the behavior of the reaction in a batch bioreactor concept, where we have time-variant conditions, discontinuous processes, and we have downtime for cleaning and filling. And here we have the operating variables. Okay, so if we want to use at this moment, then we should remove the enzyme from this reaction mixture, which is anyway costly and time-consuming. So moving to a system where the enzyme is immobilized within the membrane. In this case, we have used a very simple method to attach the enzyme, to immobilize the enzyme, which was by physical entrapment, just by fouling the membrane with the enzyme, filtering the enzyme solution from shell to lumen into an asymmetric membrane which had the selective thin layer in the lumen side, so that the molecular weight cutoff of the membrane is lower than the size of the enzyme, and the enzyme is entrapped within this spongy-like system. Then each pore, in this way, if we have a solution with the reagent that is fed to the hollow fiber capillary membrane module from the shell side, we press with the pressure, we press the solution to go through the membrane. While passing through the membrane, it will meet the enzyme, which will catalyze the reaction. And from the other side, we collect in the permeate the reaction product. Now, this we can see each pore as a continuous stirred tank reactor, which is working in time invariant conditions, and at the steady state balance equation we can estimate the reaction rate basing on the parameters that we can easily measure, okay, which is the flow rate, the flow rate that enters the reactor, and the one that goes out, and the concentration that enters and the concentration that goes out from the system. And the volume of the reactor. The volume of the reactor, in our case, is the void volume of this asymmetric membrane. In the continuous stirred tank reactor, then we have that this is the amount of the reagent, the fumarate that enters the membrane, and this is the amount that exits from the membrane. So the difference is what has been converted into the malic acid. Here is the enzyme stability for the different steps experiments. So we can see that each step was run for 15 days in continuous, and the catalytic stability and the conversion and the catalytic stability is quite constant. This is done, of course, on a laboratory scale with model solutions, but it is an indication that the enzyme can be quite stable. We have that the parameters, the factors, we have been working a lot on trying to understand and trying to predict what type of parameters most influence the performance of the enzyme within the membrane and of the biocatalytic membrane reactor. And here I will list some of them. First of all, of course, we have the amount of enzyme that we mobilize in the membrane. As we mobilize more catalyst, if the catalyst can all work, then the conversion will enhance. But at one point, because of mass transfer issues, the performance of the system will level off. And if we consider in terms of observed specific activity and the catalytic activity, where the specific activity is just the mass of product over the time and normalized by the amount of enzyme that we have in the membrane, while the catalytic activity is just the mass of product as a function of time. What we have here is that for what concerns the amount of product that we obtain as a function of time, as we enhance the amount of enzyme, we increase also the productivity, basically. At one point, we will have a plateau, which means that the additional enzyme I'm adding to the membrane is not contributing to the reaction, which has a negative effect on the specific activity, which is normalized by the mass of enzyme. At a certain point, the activity can even decrease, because when there is too much concentration, enzymes suffer by crowding phenomena. And therefore, we need to work in an area where we have the right amount of enzyme in order to waste enzymes, which is quite expensive, and working at the highest efficiency. Residence time is another parameter, because as I was mentioning in this case, because the membrane does not separate the reagent from the product, we need to modulate the reaction residence time in such a way that we have enough time to the two components to interact and to be converted, and removing the product from the reaction site. So we can see that as we increase the residence time, then we can increase the conversion and the efficiency of the system up to a certain level. And if we look together to the amount of mobilized enzyme and to the residence time, here is illustrated, for example, the conversion as a function of the flux through the membrane, which the higher is the flux, the lower is the residence time, okay? And if we see each of these lines, which means that they are carried out at different enzyme concentration within the membrane, we see that the reaction rate decreases as the residence time decreases, and this effect is less impactful as we enhance the concentration of the enzyme. And about the factors related to the membrane itself, depending on the type of reaction, of course, in this case it was, in the case I'm showing here, it was an hydrolysis reaction. The enzymes in general need some water activity water activity content and aqueous environment. So we can see that the specific activity of enzyme can enhance significantly based on the hydrophilicity of the membrane. Another I was mentioning that the mass transfer can limit a lot what we obtain as a system. And in general, in the literature, what we observe is that the enzyme is attached on the membrane. There is a lot of literature on this type of systems, but the enzyme is immobilized on the membrane, and then the membrane is cut in little pieces and immersed into a beaker for having the reaction as a heterogenized enzyme on the membrane. But even though we stir the solution, the transport occurs at the membrane interface. So here what we can see is that for different membrane thickness, which means different reactor volume, as we increase the reactor volume, we increase the amount of immobilized enzyme, but the concentration of the enzyme is more or less constant. And with the increasing of residence time too. We see that if we run the reaction under convective flow, here is the results, okay, of the catalytic activity in terms of millimole per minute. But if we run the experiments under diffusive transport, as I mentioned, you maybe just simply immersing the membrane into a solution, we see that it is dramatically lower. So we hear in the literature that we know that the mass transfer is one limiting aspect in the type of experiments we see reported in the literature, but this is one of the evidence that we need to really take into account how we test the immobilized enzymes in the biocatalytic membranes in order to end up with consistent results. Now I will just very briefly illustrate some results, because the time is really running fast, on using cells, okay, in a fermenter, and then using the membrane as a separation unit. In this case, what we have here is a fermentation that was producing lactic acid from sugar, and using a lactobacillus. So what we have is a fermenter that we feed continuously as we remove the volume from the membrane. Here is used the ultrafiltration membrane, which retains the cells, but because we use sugar, this sugar, of course, is passing through the membrane along with the lactic acid. But looking at the fermentation itself, here is the results of the batch fermentation, in which we see that the glucose decreases and the lactic acid increases. At one point, once the glucose has been fully consumed, the bacteria will start to die, and we have to shut down and start up again. But if we move to a continuous system in which we have the continuous removal of the product that is formed, we can see here the optical density, which is an indication of the bacteria that continues to grow and that continues to produce lactic acid. The first two here are the batch systems, and the other, as a function of time, are the continuous fermentations at different dilution rates, which means at different residence time, basically. And thus we can see as we can quite work at very high cell density and at very high performance. The subsequent problem in this case, in this system, is that we have the product in a very diluted solution, okay? And then we have to still separate it from the glucose. Here we have tested very long ago a membrane-based solvent extraction system in which we had two membrane modules, and we had in the feed, we had the lactic acid coming from the fermentation broth. Then we had an organic solution with a carrier, and from the other side, we had a stripping solution. So what we have here is that the lactic acid will bind to the carrier, and then it will release from the other side basing on the affinity created by the pH. And what we have, just to show you the results, is that if we have the separation from aqueous solution and from the fermentation broth, of course we have a difference because we have other materials, and the overall mass transfer coefficient is also influenced by the other components. But the system that we have used, the carrier was quite selective for the lactic acid, and we could separate it. As a conclusions, I think these systems are able to reduce water and carbon footprint because, as I mentioned at the beginning, they have a lower energy demand, at least compared to chemical catalysts. When we can efficiently implement these systems, they may have low environmental impact. Of course, they are secure, clean, precise technologies, but still, we have a number of items to still develop, and here I highlighted the most. Now, I think membranes and modules, they need to be developed a lot because we need to develop membranes designed ad hoc for the reactor. And modules as well in order to better control all the parameters, and modeling, which is one of the items that may alleviate the heavy burden of trial and error activity that so far dominates the research in the field. And with this, I would like to thank you very much for your kind attention, and I'll be happy to take any question.
Thank you very much, Lidieta, for this great talk and for the insights in the biocatalytic membranes. We can have a short question. Yeah, there's already one. Yes, Bettina, maybe you want to start first.
Yes, sure. Lidieta, many thanks. Always great to hear your talks. And
Bettina, I think we can't hear you.
Definitely interested to test.
Oh.
Okay.
Bettina, unfortunately, we cannot really hear you. Maybe until Bettina gets it sorted. Do we have a second question from the audience? I've seen a hand raised before. I think she has some problems. Yes, Dr. Chimo Coyote.
Yes. Thank you so much for the opportunity. Just a simple question. I want to ask about the concentration that you have used that prevents the issue of fouling, because I didn't see you discuss anything about fouling.
Yeah, in this case, as I was mentioning about the enzyme immobilization, we used just the fouling phenomena as an advantage to stick the enzyme on the membrane. And in the case of fumaric acid, that was a model solution. So the size of the reagent and product were similar and much lower than the membrane. So the fouling was basically tuned because as the molecule come to the membrane, the enzyme hydrolyzes, and then the convective flow removes. In the case of the fermentation, in the case of continuous fermentation, in that case, fouling is an extremely important aspect, and in particular it was dominated by the protein that were produced by the fermentation itself. That's why we had to use ultrafiltration and non-microfiltration that would be enough to retain only the bacteria but not the proteins. And in that case we had to use a system of feed and bleed to keep the protein below a certain concentration. So what we had to do in practice is that we work at low flow rate in order to do not deactivate the proteins that would create a higher fouling. And fluxes were in the range of 20 to 30 liters per hour per square meter, not more.
All right, thanks so much.
Yeah.
Thank you. We just received a question from Bettina, so I may just read it out loud on her behalf. She asks, in which sizes and configurations are the biocatalytic membranes currently available?
We have immobilized the enzyme in modules, whole capillary modules that are about 25 centimeters long in a very reproducible way. Then we have also tried to scale up on larger modules commercially available that are about less than half square meter. And we see a problem in reproducibility, okay, of attaching the same amount of enzyme and same distribution as we enlarge the size of the module. The critical issue is that we can tune these problems by starting with appropriate initial concentration of enzyme. But the point is that we don't want to waste too much enzyme. No, we want to have the enzyme in the solution that all goes onto the membrane. And in this case, we start with very diluted solutions. It takes longer, but we can have, let's say, between the 25 square centimeter up to the, let's say, 40 centimeter long, we have a 20% reduction in enzyme performance.
Thank you. I think this sounds already very promising, and upscaling is always problematic, but it seems that in the lab scale setup, it's already available, and that's very great news. So I think we will...
Yeah, we need certainly startup drivers now where we can demonstrate this for a much longer time, no? Because in the lab we are really limited by handling too large solution and for too long time.
Perfect. Lidieta, many thanks for your presentations, and I think we have to move on now. Thanks again. I would like to introduce the next speaker, which is Priyanka Mondal from V2 in Belgium. And she will be presenting about waste oil to high value chemicals.
Can you see the slide? Yeah.
Yes, now it's visible. Can also hear you.
Okay, so it's visible and you can hear me, right? Yeah. Okay. So good morning, everyone, and thank you very much for the opportunity to share our work. So today I will gonna talk about waste oil to high value chemicals, opportunity and challenges for membrane-based processes. So in Belgium, who doesn't like to eat fries? So if you are in Belgium, fries are everywhere. But the problem is it produced a lots of waste oil, which is also a burden for the environment. But what we can do is actually we can use this waste oil to produce polymeric building blocks for pharmaceutical lubricant and adhesive and powder coatings. However, the process is not so easy as the man who is preparing fries are smiling. So I will gonna discuss about some results and also the challenges in my upcoming slides. So how we deal with this issue? Actually, we have, I will make quickly to the pointer option. Yes. So there are some companies who collect actually these waste oil and grease trap waste oils, grease trap waste for this recovery, but this is not as straight as it is. So it's first go through the fermentation process where non-pathogenic yeasts are used. Before even moving to this process, we may have go for some pre-treatment steps to remove the toxicity, and after that we move for the DSP process. So during this DSP process, we mainly use ceramic ultrafiltration, membrane-based extraction, and organic solvent nanofiltration. Here we are talking about recovering of long chain decarboxylic acid, not short, not medium. So long chain basically starts from carbon length from 12 and upwards. So the nature wise they are a bit different. They are very hydrophobic and they are challenging and as well challenging for recovery. So first I will talk about the pre-treatment of this grease trap waste. How we did this one. So as you can see that first we need a conditioning process to make this waste oil for efficient for the fermentation. And in this case, this waste oil are actually lipid rich and low value waste stream, but can be a promising feedstock for LCDA production. Limitations for this one, as you can see, this in the left hand side picture, that is original grease trap waste, which is really very thick. So we had to go for the higher temperature to deal with this high viscous one. How we will deal with this high viscous grease trap waste? We first go to higher temperature and then we use our in-house ultrafiltration unit that is present together with some ceramic membranes. So we screened several ceramic membranes to remove anionic surfactant and the trace metals. And there we found that the zirconia and titania based membrane are working quite well. They are both from Innofor, or there is also one grafted membrane variant in vitro in-house we have that we tested for this pre-filtration step. This is the result of what we obtained after this pre-filtration step. As you can see that we were able to remove around 90% of surfactant by using 3 nanometer membrane. Among those 3 nanometer membrane, we have the C1 modified membrane that is prepared in vitro that gives almost 7 times higher flux than the normal 3 nanometer membrane. And the main principle for this high metal removal efficiency was because of the adsorption of the membrane together with interaction between anionic surfactant and positively charged metal ions. Now the next is how this pretreatment affect on the fermentation process. As you can see that the blue bar is actually the untreated grease trap waste and the red bar is the treated one. So there you can see that the outcome was quite good. So we got around 25% higher titer production, 10% higher productivity rate, and high lipid to LCDA conversion rate. However, the remaining challenges, as usual, the membrane fouling. But as a whole, we can conclude that the pre-treatment ceramic ultrafiltration membrane enable to produce LCDS production, which can also support the valorization of the lipid waste. So next is actually proceeding for the DSP train. To design this DSP train or isolation of the purification of LCDA building blocks, we know that there are several usual process has been followed. So we have the fermentation broth, then you can do like cell removal, then recovery of LCDA, further purification and concentration, and at the end is the separation. Separation is actually very important and it is must required for high value applications of these long chain decarboxylic acids. There are some state-of-the-art processes are available mainly for shorter and medium chain carboxylic acid, such as precipitation, solvent or reactive extraction, pressure-driven membrane filtration. And some processes available for purification is mainly the affinity processes, such as distillation, evaporation, chromatography, adsorption, and electrodialysis. But what are the approach that we in vitro we took about? So we took a bit of slightly different approach. There we wanted to club up 3 processes in one process. So the cell removal, recovery of LCDA, and further purification, we wanted to club 3 process and use membrane-based extraction process. Before proceeding directly to the membrane-based extraction process, we first screened some solvents via using Hansen solubility parameter, that is called with a predictive stage. Then we move for selection of extractant and influencing conditions that we also performed by some small scale, but in a large variant of liquid-liquid extraction experiment. And after that, we select the right few solvents to go for membrane extraction experiment. And further, when we are working on the membrane extraction experiment, we also modify the conditions and to adapt with the process of the fermentation broth process and the full chain. So, and the further step was also very important, that is the back extraction and further separation. So we proceeded first with the model mixture, and then we move for the real fermentation broth. But today I'm going to show the results all about with the fermentation broth. So before proceeding to the actual result, I want to say something about what is the membrane extraction. Membrane extraction is basically a contactor application where membrane just acts as a support layer where we use microporous membrane. And these microporous membrane are mainly hydrophobic in nature. The driving force is mainly concentration difference, and adsorption, diffusion, desorption, these 3 processes follow simultaneously in this case. The advantage of this membrane extraction, actually, the solvent with the low biocompatibility can be used, and the emulsion formation then in usual liquid-liquid extraction cases can be avoided. However, since we are talking about long-chain decarboxylic acid, indeed we saw some difficulties with using the usual membrane extraction process, and for that we also tried another finer version of membrane extraction process, which is tight membrane extraction, and we call this as a game changer because, as you can see later, that it really have some advantages. So what tight membrane extraction can do is, as usual, that it increases the interface stability because long-chain decarboxylic acid shows some weighting on the membrane of usual hydrophobic porous membrane extraction membranes. Together with that one, the tight membrane also adds selectivity using solid membrane affinity and solid diffusion. And the steering the affinity by selecting right modified ceramic membrane, we use Fraunhofer modified membrane and also Vito in-house membrane. And we can also work in a solvent-free mode, that is the supported liquid membrane module, where you can immerse the solvent inside the membrane. But this process is also comes with some limitations, and main limitation is the extra resistance and fouling. So then how we proceeded, first we go for isolation and purification. So first we go for some liquid-liquid extraction experiment to screen the whole process. So we have our fermentation broth that from our partner university we received at fermentation at around pH 6. So that is the ideal condition of the fermentation, and there we found we performed physical extraction and reactive extraction, and there we found that physical extraction is possible only below pH, below than the pKa. But if we want to go, if our pH is above pKa, or even in the fermentation pH, the reactive extraction is much better to reach more than 90% recovery. And that's why we decided to go for screen again. As you can see here, the result, what I mentioned in before slide, that we found that ethyl acetate, octanol, and decanol 3 suitable physical extractant or suitable solvent to test with. And there we found that these solvents shows some selectivity for some of the components, that are present into the fermentation broth, both saturated and unsaturated LCDs. But the thing is, the recovery was near about 50%. However, our target was to reach recovery around 90%. And to reach this recovery, we need to go for reactive extraction. So that's why in the membrane test, we first move for the reactive extraction, but also during the whole screening of the pH study and also during the liquid-liquid extraction, what we observed, that during this process, we found the co-extraction of the free fatty acids, which is quite obvious because their fermentation broth are directly coming into the contact with the solvent, and then we, together with the long-chain decarboxylic acid, the unconverted free fatty acid which was present in the fermentation broth were also extracted together. However, we saw some preferences for LCDs and then for more stable complex during the reactive extraction. For our case, we found aliquot was the best reactive extractant. The tertiary usually used tertiary reactive extractant triactylamine, or known as TOA, was not as sufficient to reach the reactive extraction more than 90%, and that's why we selected aliquot as aliquot quaternary amine as the reactive extractant. So moving forward for membrane extraction results, there we first tried the membrane extraction experiment at fermentation pH, that is pH 6, using aliquot octanol. There you can see that the extraction efficiency was around 40%, which is not too high, although the process was a bit slow. But together with that one, the interface was quite stable. However, if we to increase the extraction efficiency, then we took another approach that we increases the pH of the fermentation broth, and we increases the pH up to 12. Luckily, our ceramic membrane prepared in vitro are supporting this high pH range, even with some modifications, so which is good news for us. And then there we found that the extraction efficiency was quite good and plateau doesn't reach, so it seems it's still going on. However, the process was a bit slow, as I mentioned before. Together with that one, the membrane also shows some selectivity towards some of the decarboxylic acids, especially the 18 unsaturated and saturated 18, 16 and 14. And the best part of this membrane-based reactive extraction is that no co-extraction of free fatty acid was observed. So at a time, we are extracting LCDs out of the fermentation broth, and also the free fatty acids or unconverted free fatty acids remain into our fermentation broth. So that is a good news, but together with that one, when we all talk about extraction or more than 90% extraction, but very limited literature are available, or there are no literature almost available for the back extraction. So indeed, our reactive extraction was quite good. We could reach around 90% by variation or playing with the pH, but what about the back extraction? So when we tried several processes to get back our LCDA out from the solvent, but there we found the challenging it's very challenging to break the complex of LCDA and aliquot. And we found only with some of the pH swing case, we were able to get back 10%, but that is not sufficient. And we also saw recently, because aliquot used lots in a lot amount in case of metallurgical research field, and they also facing the same issue, and they are also recently stating that the ionic liquids are not good enough for these applications. So what we see that then we again tried our method to see whether we can able to back extract our LCDA from physical extraction or octanol or ethyl acetate. We choose octanol because octanol give a very good extraction without formation of emulsion. And then we found that it was possible to back extract our LCDA using pH swing process, and we were actually able to recover around 77% of LCDAs, which is really a good news for us. So what we learned from this one, actually, so as you can see in fermentation pH, the physical extraction performed is possible around 50%. To go more than 90% recovery, you need to go for reactive extraction. And what is the reactive extraction difference between liquid-liquid extraction and membrane extraction? So the advantage of liquid-liquid extraction that we can go around 85, we can able to reach around 85%. Whereas in case of tight membrane-based reactive extraction, we could only able to reach around 40%. But in case of membrane extraction, we were actually able to separate completely the free fatty acids and LCDA from each other. And the interface was very stable, even longer time, more than 10 days or 15 days operation, which is really very, very good for this case of fermentation broth experiments. And but the problem of this process in both cases, that back extraction from aliquot. So what we can say that first of all, no ISPR is possible, that is in the fermentation PA6, and we have to go for another alternative. So we choose another alternative approach. The approach is the first approach we choose to reduce the pH below pKa, where all of our LCDA will come up into the precipitation phase. And the first approach is we will do the liquid-liquid extraction with octanol. There we would be able to extract more than 90% LCDAs. Of course, the challenge is with this LCDA, we will definitely extract some of the free fatty acid. And how we will deal with this one? So we further go for organic solvent nanofiltration to separate the free fatty acid from LCDAs. There we really found some promising results, although the studies are still ongoing, and the preliminary results after testing few membranes, we found that around 60% or 58% retention of free fatty acids is possible. So we could be able to separate the free fatty acid from LCDA. However, we need to find the right membrane for this one, and we are currently busy with this one. And the second approach is obviously directly go membrane-based solvent extraction. What we can do in that case, that we can directly add the membrane in between fermentation broth and our solvent octanol, and we can run. We run this experiment. We were a bit worried about the precipitation issue and the blocking of the membrane, but luckily we haven't seen any challenges during the running of the experiment. And we found it was quite smooth to run the experiment, and we are currently waiting for the result to see exactly what we got. So if we are able to even remove the free fatty acid from LCDA during this test, then it could be a great news for us. Otherwise, we can also move for the further OSN experiment. And you see among the tested membranes, Borsig ONF3 membrane shows quite promising results. We are still further digging deeper into it. So the conclusion of what we learned, conclusion is pre-treatment of waste oil required to obtain higher LCDA concentration. We can remove the anionic surfactant, and we can partially remove the trace metals too. So successful removal with micelle enhanced ultrafiltration using modified ceramic membrane is possible during pre-treatment, and we can condition the fermentation broth for future. Then the second is the recovery of LCDAs from fermentation broth using liquid-liquid extraction or membrane extraction. It is a bit challenging, as you can see that the precipitation of LCDA is really a big challenge, and the solubility of LCDA almost is nothing during the fermentation broth or pH below pKa, so which is really a challenging issue. And also during that one, the difficulty of back extraction from aliquot, because extraction is not successful if we cannot back extract them. Then the case of tight membrane extraction, the advantage and disadvantage is we can separate long-chain decarboxylic acid and free fatty acid by using tight membrane, but the precipitation of LCDAs it's reduced and the process is a bit slow too. So as a whole, what we found that the membrane-based reactive extraction works better than membrane-based solvent extraction, but back extraction is challenging. So we need to bit balance between that, or we need to fine-tune there. And partial separation of LCDS and free fatty acids is possible using organic solvent nanofiltration. So no research is finished without lesson learned. So what we learned during our this fermentation broth ongoing and finished projects, the development of DSP is really very nice, but it is very important that we develop this DSP together with the fermentation broth. Because it often appears that the fermentation broth optimization is still going, and then our time is running, and then the fermentation reach to us for optimization or designing the DSP, and we have very limited time for that one. And each time during this optimization step, fermentation broth change their composition, and that really hampers our designing our DSP train. Another thing is not everything can be solved by DSP. So you also have to consider the source. So waste oil, which is really a mixture, which is very nasty, which is a mixture of free fatty acids and other products. And then we can always get a mixture of LCDs. And these long-chain decarboxylic acid, for example, 16 and 18, they really have a similar type of property, and which is almost impossible to separate from each other. And variation in feedstocks, that is waste oil, implies that the variation in LCDA mixture, and it is really difficult to reach to the certain purification level. However, we can always get a mixture of purified product. And remaining free fatty acids and tags are complicating this DSP tremendously. So optimization of fermentation is also a key factor before reaching to the DSP train. And reactive extraction with ionic liquid, we can definitely reach to higher extraction efficiency, pH above the pKa, but back extraction is extremely challenging due to the stable complexation. So along with this one, I want to thank you for giving this platform, and along together with University of Antwerp, Ghent University, and the funding agency. And that's all from my side. Please, if you have any question.
So thanks a lot, Priyanka. It's a very interesting research you presented today. We have time for maybe one or two short questions. Yeah, there's still some applause coming. I think I can maybe have a very general question. What is your targets from now? So, now you have a very good overview on what is possible and what is not possible. What would be your next steps now in terms of waste oil to high chemicals? Would you?
So for us is actually now we almost now we know, because we tried different DSP strains, and no matter whatever the pH. So first our target was the ISPR, in situ product recovery, but then we find the challenges for long chain decarboxylic acid in the fermentation broth, and we found that ISPR is not possible. But indeed it's possible if we play a bit with the pH, because we have the right membrane who can work in the certain pH, even in the lower and higher pH range. So we have the right tool to work further. But indeed, as I say, that the project is almost finished and we reach up to this one, but we are actually ongoing with this one, and we are looking forward with for the future. So, and I hope that maybe not a reactive extraction, but actually the chemical extraction will give much better solution, and this is better in if we.
Sorry, now I think there is a problem with your connection. I cannot really hear you. Just got more quiet. There is another question from the audience I just found in the chat, and I just read it out loud now. Why did you particularly choose ceramic membranes? Now we cannot hear you now. Priyanka, there is a problem. No, I think your microphone died. I'm sorry to say that, but you're not muted, but we cannot hear you.
Can you hear now?
Yeah, now it works. Yeah.
Oh,
Maybe
I'm
you
so
just
sorry.
want to comment on the question why you chose ceramic membranes for this.
Yeah, for the polymeric membrane, actually the usual polymeric membrane that are available for membrane extraction experiment, they shows wetting. They are usually porous and they are very good for the shorter chain, and you can see a lot of publication they use that one. But in a real case, when we have long chain decarboxylic acid, it shows wetting issues. In fermentation pH, I must say, because in fermentation pH, they stay both as dissociated and undissociated phase. That can help, that can maybe affect on the membrane property. And that is the reason we move towards the ceramic membrane, which works very well for us.
Okay, thank you. I think we have to move on at this point. So thanks again to Priyanka for the nice talk. The next speaker is Alexander Drischak from Institute of Chemical and Environmental Bioscience from the TU Wien.
Hello, everyone. Can you hear me and see the presentation, my screen?
Yes, it works.
Okay.
Thank you. Floor is yours.
So yeah, thank you for giving me the opportunity to present mine and my colleagues' work in the development of a hybrid membrane and adsorption process to improve the decolorization of starch hydrolysis. So in this work, it was mostly focused on glucose syrup, which is probably the main hydrolysate obtained from starch. It's defined by EU and World Health Organization as a purified concentrated aqueous solution of nutritive saccharides obtained from starch and or inulin. It's widely used in food and beverage because of its consistency, its volume, flavor, and to improve the stability. And of course of the sweet taste. And furthermore, it's also used in pharmaceutics, fermentation processes, for bioplastics and building industry. And yeah, it's a very widely used product. And from the 8.3 million tons of starch produced yearly in the European Union, nearly half of it is used for these saccharification products such as glucose syrups. Yeah, it's produced by so there's two ways. One is dry milling, one wet milling. Dry milling is used mostly for ethanol fermentation. In this case, we focus on the wet milling process for native starch. There are also some other side products such as fibers and proteins are in the starch. And then in an enzymatic conversion, the sweetener, the glucose syrup is produced. And this enzymatic processing consists of two stages. The first stage is the liquefaction, gelatinization and the liquefaction. That is mostly done in one step. Hereby we have 105 degrees Celsius for 90 minutes, and in a next step, the oligomers obtained from the liquefaction are broken down to monomers in the saccharification, which can last for several days. And hereby, so we attain our glucose syrup. But hereby the problem is that due to these temperatures during this processing and this long processing, mostly Maillard reaction and also some caramelization occurs, and therefore we have a brownish color with a specific taste also to this Maillard products. And therefore here nowadays or mostly in industry, decolorization process is carried out to remove the color to get a colorless product that can be applied, can be widely applied in different products without affecting the appearance, and also to remove some taste. And therefore mostly activated carbon is used and ion exchange resins. And here comes now our research. The question if we can replace this ion exchange resin, also because it's prohibited in organic products, by implementing a membrane process before the activated carbon, and also possibly affect the overall process positively by saving because if we only use activated carbon, we need a lot of activated carbon to obtain this colorless syrup, and also to affect this in a positive way by saving some of this activated carbon by the preprocessing. And therefore, first, so the raw syrup was we got with 70 bricks, so it was highly concentrated. Therefore, we diluted it to several dilutions of 16, 20, and 40 bricks. And first, we carried out a deep investigation of the activated carbon process to see where are the optimal conditions, and generally how this adsorption process behaves. And then we select our baseline process and tested several membrane multi-stage processes as a pre-treatment before this baseline activated carbon process, and see how this membrane process affected our required dosage to obtain the final colorless product. For here, the methods, the glucose syrup was provided by Agrana, Austrian sugar production company. We used as an adsorbent activated carbon from Norwich. That's a very commonly used activated carbon in this industry, and we estimated the color of the solution by the ICUMSA method, which is the international standard for the measurement of color in sugar products. And here it's defined by the absorbency at a wavelength of 420 nanometers times 1000 divided by the cell length and the concentration of total solids. And also the sugar is estimated by the refractive index, by the commonly used bricks unit, which is 1 gram of sucrose per 100 gram of solution. So, and for the analysis of the adsorption process, first for the equilibrium analysis, the isotherm models Henry, BT, Langmuir, and Freundlich were used, and for the kinetic analysis, the film diffusion model and the intraparticle diffusion model were applied on the dataset to see where it fits best. So first, I want to present you the results from the adsorption, and later then from the membrane process. Generally, we have that the BET isotherm was fitted best. So this and the curves show the Huber classification of type 3 isotherms. This says us that we have a multi-layer adsorption process, which means we have a very strong interaction between the color molecules itself. What we also can see in this curve is a small curvature at the lower concentrations, which goes more into the direction of type 2 isotherm, which means we have a prior monolayer adsorption in our adsorption process, especially if we used higher diluted syrup, which can be explained by the greater distance of the color molecules. They don't interact that strong anymore, and are absorbed first as a monolayer. So to the optimal dosage to get our baseline optimal conditions. Here the dosage is estimated by the point where no significant change in the dosage occurs anymore. What should be mentioned here, that the blue line, the 30 bricks concentration, was a different batch. That's why it's behaved a bit worse generally in decolorization. But what we can see that with lower sugar concentration, we require less activated carbon for decolorization, so to obtain our final optimal stage. However, the sugar is our main product. Therefore, hereby it's more interesting to see how much activated carbon is required, dependent on the sugar obtained in the end. Therefore, a relative activated carbon dosage was estimated, which was divided by the Brix, by the sugar concentration in the solution. And here we see clearly the orange curve with the highest sugar concentration shows the least required activated carbon dosage. So we know now for most efficient process, we require a very high concentrated solution. However, this would also lead to higher viscosity and may other problems in the processing. So this has to be also taken into account. And for the time required, on the left we see with more time, with more sugar in the solution, we need more time to obtain the equilibrium state in the adsorption. Probably can be expected to do higher viscosity, higher concentrations. And also on the right side, we see with for same concentration, we see with higher activated carbon dosage, we require less time. Also, probably due to the fact that with higher dosage, we have a greater surface area and therefore more interactions and therefore a faster process in general. However, we can conclude that for our baseline, we can see that probably 30 Brix generally, so 40 Brix was already difficult because of its viscosity, therefore probably 30 Brix also in terms of time, and the dosage would be the best case for our baseline adsorption process. And also the modeling of the adsorption. Generally, we see it was a very fast process, very fast initial process. The state of so we have a very fast initial process and afterwards a more slowly process, and generally the intraparticle diffusion model fitted better, meaning this is our rate limiting step. This can be taken into comparison by the Beard number, where greater Beard number means intraparticle diffusion is more rate limiting, while a lower Beard number means that film diffusion also plays probably more bigger role in the rate limiting step. And what we see here from here is with lower concentrations, the intraparticle diffusion becomes slightly faster, so film diffusion becomes more and more relevant. But however, generally film diffusion was very fast, so not a comparison to the intraparticle diffusion speed. And then the last question for the activated carbon is, do we lose some sugar during this process? Generally, there was a sugar loss of around 5 to 6% during this adsorption process. Hereby to know if this is because of our activated carbon or maybe some other defiltration process to separate the activated carbon from our solution. A blank was carried out, only filtration, and the full process with adsorption and filtration. And what we see, if we only do the filtration, we have a similar sugar loss as with the overall process. So we can conclude that the main cause of sugar loss is probably the filtration to separate our activated carbon, but not the adsorption itself. Now to the membrane process to possibly improve this adsorption process. Hereby 7 different configurations of membrane processes were tested with 4 different membranes. There were 2 ultrafiltration membranes, one with 100 kilodalton, one with 5 kilodalton, and 2 nanofiltration membranes, one with 100 to 300 dalton, and the tight nanofiltration also with 100 to 300 dalton. And the first 2 configurations consisted of 3 stages. First loose ultrafiltration, then a tight ultrafiltration, and then the tight nanofiltration. And hereby the difference was that the first process was carried out with additional dilution after the first initial loose ultrafiltration to possibly improve the tight ultrafiltration afterwards. And then the tight nanofiltration was mostly used to concentrate the diluted stream to the 30 bricks, which was our baseline for our activated carbon decolorization process. Then the same configuration was tested without the loose ultrafiltration in a two-stage setup. So two different feed concentration of 20 and 30 bricks. And then also one setup was tested with tight ultrafiltration and loose nanofiltration. Hereby the rate and tide of the loose nanofiltration was only 15 bricks because it was not working as it was expected. And this same setups, or this two-stage setup, was also tested with a defiltration by 3 defiltration steps for tight ultrafiltration and nanofiltration. Each setup was diluted by one, so 1 to 1. And also only the nanofiltration was used to possibly remove some other byproducts by the nanofiltration into the pyramid to see if this affects our adsorption process. So to compare these results, first the baseline concentration dependent on normalized on the sugar concentration in the solution. The dosage, activated dosage normalized on our sugar concentration in the solution to obtain a color below 45 Ecomsa units, which is probably so is nearly colorless, was compared to the dosage required after the preprocessing to obtain the same colorless syrup. And what we see here, especially the configurations which included the tight ultrafiltration, so the 5 kilodalton ultrafiltration and the nanofiltration performed very good. So they were able to reduce the required activated carbon dosage by more than 50%. And especially in this setup 2.1, which had 20 bricks feed into the tight ultrafiltration and tight nanofiltration, was the best. And to see here, compare here the detailed results. On the left, we see the behavior of color with applied dosage. So with higher dosage, so with the blue line, with the preprocessing, we obtain already at very low activated carbon dosage a very colorless or a product with very low color. And also on the right, we shifted the equilibrium more to the adsorbent side, so more is adsorbed onto the activated carbon by this preprocessing. Also, yes, we have less color in the feed to the adsorption process. However, the color obtained in the lower activated carbon dosage is that the difference is greater. Therefore, there is also other improvements. Maybe other impurities were also removed, improving the adsorption process. And now, last, a short cost comparison to answer the question if such a process is even economically feasible. And for this, a continuous process was designed to produce 1,000 tons of sugar per year. And there were 2 reactors were used. So one is filled for 1 hour, where the adsorption is carried out, while the other one is emptied into the vacuum filtration. So this is switched every hour to obtain our continuity. And hereby 8 kilograms of cubic meter activated carbon were used. And then the other process, the ultrafiltration and the nanofiltration membrane process were added before the absorption. And hereby only 2 kilograms of per cubic meter of activated carbon were used. However, hereby The stage cut was set at 80% for the ultrafiltration and 50% for the nanofiltration to have our 30 bricks solution for the activated carbon adsorption. And we had here quite high loss of sugar. So this needs to be, this we can discuss on the next slide. So first, what we see here, dependent on the activated carbon price. On the next slide, when we put the total costs of the process, comparing to the activated carbon price, the additional membrane, the investment in this additional membrane process leads to less activated carbon, and this additional costs are lower, especially if we have activated carbon price above 0.1 euros per kilogram, so 20 cents per kilogram. The investments into the membrane are leading to a more cost efficient process. However, what is not included in this calculation is that due to this sugar loss, we require more feedstock to obtain the same amount of final sugar product. Therefore, in the future, the defiltration and the recovery of this retentate stream, sugar-rich retentate stream, needs to be addressed to improve this process. So, what is the final conclusion? First, to the absorption, we have a multi-layer absorption process. So, meaning we have strong bonds between our color molecules. So we have pore and surface diffusion are our rate limiting steps, and the activated carbon separation doesn't absorb any sugar, but the separation process to separate this activated carbon can have impact on the sugar loss. And for our hybrid membrane and adsorption process, we can say that with tight ultrafiltration and tight nanofiltration, we obtain great results and reduce the required activated carbon by more than 50%, which is a lot. And this is, of course, economical feasible, especially with higher activated carbon dosages. And in future, the sugar losses should be addressed so not that much feedstock is required, probably by defiltration and sugar recovery. And with this slide, I want to thank everyone very much for your attention, and I'm open for questions if there are some open questions.
Perfect. Many thanks, Alexander, for this great demonstration of membrane use for decoloring of sugar. Do we have any questions from the audience? Yes, Priyanka, please. I think you just have to unmute yourself. I think we cannot hear you. Can you try again, please? Aha, okay.
Can you hear me?
Yes,
I think.
yes.
Yeah, I was just seeing that you have the option for the diafiltration. Have you tried with the diafiltration to challenge this issue, or?
Not yet. Actually, this is a working process, but you mean that to see how it affects the costs?
Yeah, exactly.
Not yet in detail, but it's a working. It's currently a working process. But I expect the effect not to be too high, because the mass stream for the diafiltration is not that big anymore when compared to the initial feed stream. So the effect of additional membrane costs should not be too high.
Yeah.
Maybe if I may add, actually, Priyanka, this is a very good question. We have another talk later on by Camila Cabeza, who also worked on the decolorization. So I think maybe she can clarify a little bit more on that. And also we did long-term studies. So
Okay, perfect.
There will be
Thank
more
you.
on that.
Thanks a lot.
You're welcome.
Perfect. Thank you, Michael, for addressing this. Are there any more questions to Alexander? If not, then I would say we go on a short break, and then I'm very excited that we will start the first pitch session at around 11:15, chaired by Michael.
Okay, so welcome back. So for the first time, we try a pitch session here as a new way to briefly introduce you to an interesting and exciting PhD thesis. But before, a short announcement: do not leave the session immediately after the last talk, but stay a little bit online. Switch on your camera then. And we would like to make a screenshot also for reporting and also to seeing all of you that are online. It's more than 40 of you. That would be great. So this is just a very brief announcement. Christoph will take a screenshot. So for those of you who have not problems with data related issue, we will use the screenshot actually for reporting to our funding agencies. But that would be great if you are available for that. So without any further ado, we have now a set of very short talks. So that's each of these is 5 minutes plus 2 minutes of discussion or Q&A. And we call this a pitch session. There will be three pitch sessions actually, that one hour just before lunch. And the first one is called Membrane Applications for Resource Recovery and Side Stream Valorization. And without further ado, I'd like to announce Usman Khan from the Lappeenranta University of Technology in Finland, and also with contributions from the Technical University at Twente. Usman, the stage is yours.
Thank you, Professor. Thank you. Just kindly confirm that my laptop screen is visible. Yeah. Can you see my laptop screen?
Yes, we can see it, but not yet. Yes, now.
Okay. So,
yeah.
Should we start?
Works well. Yes, please.
Yeah. First of all, thank you so much for the wonderful talks earlier from all the professors. And yeah, now I will start my presentation, which is titled Membrane-Based Recovery of N-methyl morpholine N-oxide from Live Cell Evaporator Stream, Performance Evaluation of Nanofiltration and Reverse Osmosis Membrane. I will start my discussion from the most abundant biopolymer on Earth, which is cellulose. Now, to make useful products out of this cellulose, we dissolve the cellulose into a suitable solvent. And based on this solvent, the process of dissolution is categorized into two categories: derivatization process, in which we basically change the chemical structure of the cellulose to make a useful product, and the state-of-the-art process that is currently most widely used is the viscose process. However, the drawback of this viscose process is that it is an open loop process and it generates a lot of chemical wastes. However, for the non-derivatization process, the light process or a sustainable process or environmental friendly process is the live cell process. Now, what it is in this process, we basically use N-methyl morpholine N-oxide as a solvent to dissolve the cellulose. And how it works, as you can see on the left side, we have the cellulose chain, and on the right side, we have this N-methyl morpholine.
Osman, may I interrupt? I can only see the first slide. It's still on the first slide. Can you switch to the next slide, please?
Yeah, I am on the next slide.
No, we don't see that. I don't know which screen you share. Maybe you leave the presentation mode and just switch in a preparation mode through your PPTX.
Maybe. Can you see my PPT now?
Yes. That now we see this. Maybe you stay with this because the presentation mode doesn't actually show.
Okay, so I will.
So you should move
continue.
just to the second slide or to the one that you were just explaining.
Yeah. So as you can see, we have this polymer of cellulose, and when we dissolve this cellulose in this solvent and methyl morpholine N oxide, it basically forms hydrogen bonding with this cellulose structure. And you can see in one of the studies, it shows that we have this cellulose chain, and this solvent basically enters into this chain, and it breaks the hydrogen bonding that is within this cellulose structure to remove the crystallinity, and then we make the fiber or whatever the product we want to make out of it. And the good point or the positive point about the life cell process is that it is a simple process, environmental friendly process, and also it is a closed loop process that we can recover back this N-methyl morpholine oxide. And there are some series of processes that we use like air flotation, ion exchange, and multi-stage evaporator to recover this NMMO. However, the drawback is during this multi-stage evaporation to concentrate NMMO, we have the loss of this solvent while co-evaporation with water. Now, the thing is, in one of the studies, they have found that if the NMMO recovery is reduced from 99.7 to 98.9%, it will result in increase in NMMO makeup cost to 5.4 times. So even a slight decrease in concentration would lead to increase in made-up cost. So the objective of this research is to recover this NMMO loss in this multi-stage evaporator. However, it is dilute stream, still we want to recover this NMMO. So basically the methodology is divided into two parts. One is the chemical stability test and second is the concentration test. In the chemical stability test, we pour the membranes into the 28% of NMMO solution, and then we check the pure water flux and the model solution flux and the retention. And we have these model compounds here, some sugar compounds. And now coming towards the results for the chemical stability, on the right hand side you can see this pure water flux, model solution flux for RO and NF membrane that I use, diesel AG and diesel DK. So for extended period of time, I poured these membranes into 28% of NMMO solution, and for 0, day 28 and day 288, we have relatively the same flux for both the membranes, and also for the retention of these model solutions, there is no significant change, or they're almost the same retention for these model compounds after 288 days of immersion into this 28% of NMMO solution. Similarly, for this chemical modification to check, we performed this Fourier transform infrared spectroscopy, and there was no deviation in the peaks. So we confirmed that there is no chemical modification in the membranes that we were using. And now for the concentration test, when we applied those membranes to concentrate the NMMO solution, you can see on the left side we have the two NF membranes, on the right side we have this RO membrane. The rejection for both types of membrane was linear, constant, and there was slight reduced rejection compared to this RO membrane, and we concentrated the solution until 9% for these membranes. However, there was slight leakage for this NF270 and diesel DK for NF membranes. However, very slight leakage for this RO membrane when the concentration was very high. So with this, I will conclude my presentation that the NF membrane and RO membrane has the potential to concentrate and to recover this NMMO from the live cell evaporator stream. And as a part of future recommendation, we can replace the conventional recovery process of NMMO with the membrane-based processing. So with this, I would say thank you so much for your. If you have any question, I am available.
Yes, thank you very much, Usman, for this very fast walkthrough. Your very interesting topic. There is time for a very short question? seems not the case. I have a very short question regarding membrane stability. Has this ever been an issue? Because NMMO is also a very strong solvent. I mean, for celluloses, of course.
Yeah, we checked the chemical stability of the membranes by putting the membranes into the 28% NMMO solution, and then we checked the pure water flux and the model solution flux, whether we have a change or change in pure water flux or retention of these model compounds, or we have this chemical modification in the structure of those membranes. So after having the chemical stability tests, we confirmed that we don't have any chemical modification in both the NF and RO membranes.
Okay, so long-term stability is still an issue, but I believe that is a very promising finding, and very good luck for your continued research, and all the best for your PhD thesis. Now let's quickly move on to the next presentation by Mauricio Pane from IEA INTEC, Advanced Membrane Distillation for Circular Economy and Industrial Water Recovery. Actually, this presentation is pre-recorded, and Christoph, please let it run.
Do you see it already, the screen?
Yes, we can see that.
Good morning, everyone. My name is Mauricio Pane from IEA INTEC, and I'm also a PhD candidate at TU Vienna. Today, I will briefly present to you my PhD project, Oscillate for Cycle, which aims to improve membrane distillation for industrial water recovery. The PhD has started last year in October and builds on an earlier work from the European Cornerstone project, where we actually started exploring the potential of oscillatory flow conditions in membrane processes. Well, when we talk about industrial water challenge, it's well known that many industrial sectors require large amounts of water, and at the same time they generated complex wastewater streams that can possibly contain high concentrations of particles, organics, or even processed chemicals. These streams, they are particularly challenging for the membrane systems because they lead to fouling, polarization, and offers an unstable flux performance. However, membrane distillation is still a promising technology for water recovery and resource valorization, but its performance is still limited under these harsh conditions mentioned previously. And one key reason for this is hydrodynamics, meaning how the fluid flows close to the membrane surface. Based on that motivation, we built our oscillatory flow enhanced membrane distillation in our institute, where you can see in the right-hand side of this slide a picture of the plant. And the idea is to investigate how oscillatory flow conditions can improve membrane distillation performance overall. So, in our system, oscillatory motion is superimposed on the feed net flow using a piston-driven oscillator. The key effect is that this particle motion becomes partially decoupled from the feed flow velocity, which enhances mixing close to the membrane surface. And as a result, this approach can improve mass transfer and reduce polarization effects, which, as mentioned previously, are major limitations in membrane distillation. And based on that concept, the PhD follows the following approach that can be a combination of experimental work, modeling, and industrial case studies. First, we will operate a new oscillatory membrane distillation test plant where we investigate how parameters such as oscillation amplitude, frequency, and flow conditions affect, indeed, flux and fouling behavior. And in parallel, we will develop theoretical models to better understand the system and support process optimization. Finally, but not least, the concept will be tested for industrial applications, particularly in plastic recycling and pulp and paper wastewater streams. All the first and very promising results from the parallel Cornerstone project, we can see in the left-hand side a graphic that summarizes the permeate transmembrane fluxes obtained per experiment with and without oscillatory flow conditions. The oscillatory flow conditions are expressed in the x-axis in amplitude in millimeters and frequency in hertz, while the permeate transmembrane flux is expressed in the epsilon axis in kilograms per square meter per hour. Well, Comparing the values, we have a flux of 2.2 for the test without oscillation, illustrated in the first bar, to 4 kilograms per square meter per hour for the test under oscillation, illustrated in the last bar, therefore representing a permeate flux increase of 80%. These results suggest that flow modulation can indeed improve membrane distillation performance. So, the PhD aims to enable a more robust membrane processes for industry, water reuse, and resource recovery, supporting the transition toward circular water management in industry. Well, from my side, that's all. But before finishing my presentation, I would like to thank everyone who has been helping me in this journey, especially Professor Michael Harasek, my whole team at IEA INTEC, the European Union, Cornerstone Project, and last but not least, the Austrian Research Promotion Agency FFG for funding and supporting the PhD project. With that, I would like to thank you very much for your attention. And here you can find my contact in case of questions, benchmarking, or further collaborations. Thank you and have a nice day and enjoy the workshop.
Yes, so thank you very much, Mauricio, who is not here today, who is traveling. But maybe we can still accept questions and maybe forward it to any of us. There's a question. Yes, please. No. Mauricio is there.
Hi.
Hi, Mauricio.
Sorry. Thank you for sharing my presentation. Unfortunately, as you mentioned, I'm not in person in the office, so I don't have my laptop with me, but I just quickly took a bit of time to be present here for the questions. So I'm happy to answer any questions.
Thank you very much again for your exciting overview and also, of course, good luck. We are in touch. Good luck with your good luck with your future endeavors and with your PhD thesis. And maybe there's a question from Bettina. No, okay, okay.
Yeah, I would also take the opportunity to thank you, Bettina, because she's also my co-supervisor in the institute. So basically, I didn't mention in the video because 5 minutes is too short, but this PhD is funded by the FFG, and we have this coal industry Nachdissertationen, and I should have 2 supervisors, one from the institute where I work for, so IEA INTEC, but also one from TU Vienna, which in this case is you, Michael. So yeah, thank you very much as well, Bettina. And yeah, I didn't expect to have this first presentation of my PhD in this way recorded. So, but I'm sure new one will come, and I hope you guys
But
can be
Mauricio, because you're online now, Lidieta, I think there's a question.
Please.
Lidieta, please go ahead.
Yeah, please. It would be a pleasure.
Lidieta, can you unmute yourself? Unmute yourself, please. We cannot hear you.
Yes, now I can. Now we can
hear you.
Sorry.
Great.
Thank you very much for the presentation. I just have a curiosity. In the last slide, now you have shown the increase of flux with the increasing of the hertz, of the amplitude, and so on. With the ionized water, is it just pure water or is it a solution?
It's just a pure water, so DI water.
Which means
in the feed stream, we use the DI water, and in the permeate DI water with spiked concentration, so we can follow the conductivity in the permeate over the experiment to see the transmembrane fluxes as well. But in the feed, as we can see in the graphic, was just DI water.
So this means that the oscillation, rather than the motion, probably is the temperature that you better control due to this oscillation?
Correct. So the oscillation happens in the feed flow, and and of course this is just for DI water. We also had some experiments with industrial water in Cornerstone project, but here I just took the opportunity to bring the DI water because it's more related to the PhD project. Yeah.
Thank you very much, and success with your work.
Thank you so much. And also just a short reply to this question. The idea is that we try to use wastewaters with high solid content so that the oscillation can indeed enhance the performance, hopefully. So the DI water, as we don't have solid, it enhances, but not the main goal of the PhD in general.
There was one another question from Chimo. You may have just a quick question, please, if you like.
Yeah, thank you so much. Actually, it's similar to what has just been addressed now. That's why I lower my hand, actually. So it's answered.
Okay, thank you.
Thank you.
And the last one by Cici, please. Cici Poo, if you want, you may raise the question. Oh, sorry. Okay, there is no question anymore. So with this, actually, we are also on time for the next presentation by Sare Akol from Nicolaus Copernicus University in Toruń in Poland, titled Valorization of Biorefinery Side Streams Fusel Oils. Sare, the stage is yours.
Hello, thank you so much for the introduction. I hope you can see the presentation.
Yes.
Okay. Good morning, everyone. My name is Sare, and I'm second-year PhD student at Nicolaus Copernicus University. And today I will be presenting the valorization of biorefinery side streams, fusel oils. Did the page change? Can you see the second slide? Okay, thank you. First of all, I would like to start with a brief introduction. Fusel oil is a byproduct of bioethanol production, and its global production capacity reaches up to 1.3 billion liters per year. Fusel oil consists of higher alcohols and mainly isoamyl alcohol, which can be used in ester production or as a solvent. So it's a valuable mixture. But there is a downside of the fusel oil, which is its high water content. Because of this water content, its energy value decreases. Also, it becomes challenging to isolate alcohols. So to look at it in a bit detail here, as you can see, the boiling points of alcohols differ significantly. So it's easy to separate them by distillation. But with the presence of water, alcohols create azeotropic mixtures and their boiling points convert each other. So it becomes challenging to separate them. To unlock full potential of fusel oils, it's important to dehydrate them efficiently. By saying that the aim of this project is to implement hybrid process for the dehydration and valorization of fusel oil. For this, we have 3 steps approach. First, the dehydration of fusel oil by preparation, followed by the fractionation by distillation to obtain pure alcohols, and then further valorize them to produce higher value products. For the dehydration step, preparation process is chosen because it is not limited by the vapor-liquid equilibrium, so it's a good alternative to separate azeotropic mixtures, thanks to its solution diffusion mechanism. In this mass transfer mechanism, the desired product or compound, which is water in our case, are selectively adsorbed on the membrane surface and is diffused through the membrane matrix by the driving force of difference in chemical potential, and is desorbed on the permeate side under vacuum conditions. For preparation, mainly ceramic and polymeric membranes are used. They both their advantages. For example, ceramic membranes show higher flux, and on the other hand, polymeric membranes shows higher selectivity. And in this project, I will use both of them. To start with my results, first I start with the preliminary experiment using the ABE mixture, because ABE is a good model solution or model mixture for fusel oils because it is complex and multi-compound. Also, it has azeotrope formation inside. So I started with the PVA-based polymeric hydrophilic commercial membrane. And Sorry. Yeah. Here we see on the right graph that the water content of the ABE mixture decreased from 20% to 5%. It is possible to dehydrate it further, but for the preliminary experiment, the 5% was enough for me. Also on the orange line, we can see that the membrane was highly selective towards water, so it was an effective separation. After dehydrating the ABE, I continued with the distillation. Here we have acetone-rich and ethanol-rich phase. And as a remnant, we have a relatively pure butanol, which shows us the fractionation after dehydration is more effective. And after proving our point with the preliminary experiment, I continued with the fusel oil dehydration. Here on this table, we can show in more detail the compositions of the initial and final fusel oil mixtures. Here on the right graph, the water content in fusel oil decreased from 18% to below 2% of water, which was enough dehydration for this case because then I don't have any azeotropic mixture formation problems. And also on the orange graph, orange line again, we can see that the selectivity of the membrane is high towards water, so it was an effective separation. So after completing this, I will do the same preparation with the ceramic membrane to see the differences of these membranes, and then continue with the distillation to obtain alcohols in their pure forms. And to sum up this presentation, I would like to emphasize that the preparation is an effective method to separate azeotropic mixtures. And when it's combined with the distillation, it improves the separation efficiency. And it enables to valorize fusel oils. So this is all from me. Thank you so much.
Yeah, thank you very much, Sarah, for this exciting presentation. Evaporation is probably also an underestimated process, but I'm sure with upcoming and exciting new applications that will also be much more familiar process for many engineers. So, other questions? Any questions? Maybe I have a question to you, and that is about, as you say, there are two aspects, removal of water and also sequential separation options that you might have here, or combining it into a hybrid process. What are the energy benefits that you may see when, have you looked at that so far, or will that be a topic also?
Yes, it's having the hybrid preparation and distillation process benefits in terms of energy efficiency, because preparation, when we want to separate the minor compound in a mixture, preparation is more advantageous because we don't have to heat up the whole mixture up to like 100 degrees or something like that. So it starts with the high energy. Also, we cannot distillate everything because of the azeotrope formation, so we don't have the like separation efficiency in terms of distillation, and we cannot separate everything with preparation, then it will be highly energy intensive. So having this hybrid process is more separation and energy efficiency.
Thank you very much. I believe there's one more question by Timo.
Okay.
Yes, thank you so much. I just want to ask, what is the motivation behind combining evaporation and distillation? I mean, why not any other membrane processes like membrane distillation, nanofiltration? So I'm just curious.
Because of the mass transfer mechanism in preparation is more suitable for the because it's not affected by the azeotrope formation, so it's more suitable for the dehydrating this alcoholic mixtures. This is the main motivation, I can say.
Okay, all right, thank you.
Thank you.
Maybe to add, Timo, membrane distillation is tricky because of the organic compounds. They may wet actually the membrane. So that means the hydrophobicity can be overcome actually with the alcohols and the fusel oil components. So that could be a little tricky. So nanofiltration could be an interesting option. Maybe would be interesting to compare that. But very good comment.
Thank you.
Thank you.
Yeah, then thanks again for your presentation. And we will now move to the last presentation. Once more, a reminder, please stay tuned just after the end of this last presentation and the discussions to have a quick photo of all the persons online. So the next presentation is by Evangelina Papagianni, actually working together with Frank Lipnitsky at the Department of Process and Life Science Engineering in Lund University in Sweden, and it's titled "The Valorization of Hemp Seed Press Cake Using Membrane Processes for Phytic Acid Reduction." Evangelina, the stage is yours.
Thank you, everyone. Can you see my presentation?
Yes, we can.
Okay,
maybe
great.
to presentation mode.
And if I change the slides, can you see that? Can you see my slides if I change my slides?
Yeah, great. It works well. It works.
Great. So, good morning, everyone. My name is Evangelia Papagianni. I am a PhD student at Lund University. And today I will talk to you about the valorization of hemp seed press cake using membrane processes for phytic acid reduction. I think that it's very important to analyze some of the terms that we can find in the title. So one of them is hemp seed press cake. Hemp is an annual plant that can be cultivated has been cultivated for 1,000 years and has many applications, including textiles, pharmaceuticals, construction, paper production, and agriculture. Hemp has gained attention due to its high nutritional value and functional properties. It is rich in high-quality proteins, dairy fibers, and bioactive compounds, and it is widely used in the oil industry due to its favorable fatty acid profile. During the oil extraction, the solid material that remains is called press cake and is a very viable byproduct as it contains a substantial protein content. I forgot to mention that hemp is very important for my research as it is a crop that can be cultivated in Nordic climates. And here in Sweden, we're trying to cultivate more and more crops that can be used in various fields. So despite its nutritional potential, hemp seed and hemp seed press cake contain various antinutrial factors. And that leads us to talk about phytic acid. As you have noticed, dietary habits have increasingly shifted towards plant-based diets driven by concerns over sustainability, ethics, and health. However, while plant-based diets offer numerous benefits, they also come with some challenges, and that is the antinutrients. So it is very common to find phytic acid, lectins, and saponins, which can create some issues. Phytic acid, which is my main focus, is primarily found in grains and seeds, where it functions as the main storage form for inositol and phosphate, both essential for plant growth and metabolic processes. However, it is usually considered as antinutrient as it can interact with minerals like iron, calcium, and zinc, forming insoluble complexes, resulting in reduction of their bioavailability. Over time, people that they have diets that are high in phytic acid, especially in populations relying heavily on grains and seeds, can lead to mineral deficiencies such as iron deficiency, anemia, or zinc deficiency. Given the nutritional potential of hemp seed, particularly the high content of proteins in press cake and the presence of antinutritional factors, there is the need for efficient methods for the purification and recovery of the proteins. One method that seems to be promising is membrane filtration. In my case, I'm mainly focusing in ultrafiltration, which is a pressure-driven membrane process based on molecular size. In this method, we're using this method because it allows water and small molecules like phytic acid to pass through while retaining larger molecules such as proteins. In our case, we have used 3 different molecular sizes in order to see if we can have the proteins from one side and reduce the phytic acid by filtering the whole mixture of proteins. Another method that we are thinking of using is electrodialysis. Electrodialysis is a process that uses electrical field and special membranes to remove charged molecules like phytic acid from water or solutions. The membranes let either positive ions or negative ions to pass. Membrane-based methods are considered to be sustainable and efficient as they operate under mild conditions, resulting in high protein recovery. The growing demand for sustainable food processing has increased interest in the valorization of plant-based side streams such as hemp seed press cake, which is rich in proteins and dairy fibers and represents a promising ingredient source. So the aim of my project is to explore different processing strategies to reduce phytic acid in plant-based proteins while enhancing the nutritional properties. To achieve effective phytic acid reduction, the application of ultrafiltration, electrodialysis, and enzymatic treatment and extrusion will be investigated. Our approach centers on extracting plant-based proteins from agricultural byproducts, such as hemp seed press cake, with the final goal to be the formulation of value-added products like meat analogs. Thank you very much.
Yes, thank you very much, Evangelia, for your presentation. An interesting and exciting topic, and much to do, a lot of work, actually, also to establish and set up different separation processes with to be expected results. So we are very excited also to hear more about you and maybe read publications, or in one of the next conferences we may get an update. But I'm sure that there are questions, and there is one. Priyanka, please.
Yes, indeed. I have one question. It's a very nice talk and presentation. Indeed, as I saw that after ultrafiltration, you tried electrodialysis. So for get out your phytic acid. So how challenging it was, or how was the efficiency you obtained after the filtration? So that is the question I want to ask.
Yeah. Right now we are in the process of working with ultrafiltration, and that goes very well. And the next step is electrodialysis. Yeah. So it's something that we haven't worked until now. It's our next step.
Mm-hmm. Yeah, because I assume when we will have electrodialysis, your phytic acid will not only be the charged product, so there will be something else together with that one. That could be challenging to deal with. Yeah, okay, definitely. Perfect. Yeah. Thanks a lot.
Thank you for your question.
Mm-hmm. Yeah, thank you for the question and the answer, both of you. Is there any other question? If it's not the case, then thanks again, Evangelia. Thank you all presenters during this session, and most important of all, good luck. Good luck with your PhD thesis. Hope to see many papers out there, many good progress results presented in the upcoming events. And also, stay tuned with, of course, also with this IEA session here. So I think I hand over to Christoph just before the lunch break.
Yes, thank you, Michael. Thanks to all the speakers and contributors in the morning session.
Okay, hello everyone. Welcome back again to the webinar afternoon session and to the talk session 2 with the title of Membrane Platforms for Biorefineries. I'm Neda Assasian, and I will be chairing this talk session. And so I think we can start with our first speaker, Camila Cabeza from Competence Center Chase and Kelvin, Institute of Chemical, Environmental and Bioscience Engineering, my good colleague. Welcome, Camila, and the stage is yours. You can start. We can see your PowerPoint.
Thank you. Thank you so much, Neda, for the introduction, and thank you for the invitation to this workshop. So you can see the slides, right? Is that correct? Yes.
Yes. Yes.
Yes.
Yeah. So good afternoon, everybody. My name is Camila Cabeza, and today I'm going to present like part of my PhD thesis related with membrane-based strategies for sustainable purification of organic starch hydrolysates. This research was conducted under the supervision of Professor Harasek and Dr. Hamed, with the support of Competence Center Chase and the Institute of Chemical, Environmental and Bioscience Engineering, but also in collaboration with the Grana Research and Innovation Center. So our team was focused on the developing on a new separation process as a more environmental and sustainable alternative for the previous treatment of organic starch hydrolysates. We were focused on the purifying critical products such as maltodextrin, maltose, glucose, and dextrose syrups. These products are important for the food applications, pharmaceutical, bioplastics, and other industrial products. So after saccharification, these products needs purification. And the main challenges are yellow-brownish color, yellow-brownish color from the Maillard reactions, but also salt residues, protein, peptide, amino acid residues, together with other organic molecules. Previously, these products were purified with ion exchangers. Ion exchangers were banned for EU organic production as of January 2022, which were very challenging for the industry at that time. Together with this regulatory driver, we also were looking forward for a transition for a more sustainable technology, aligns, of course, with the global and European sustainability agendas. So this project was divided in different phases to identify also the best method for the purification. So first, we did a strategic literature review to identify the available membranes sustainable for the application, but also we developed like a survey for to select the membranes available in the market. It was important, this phase, because we also need to identify the membranes that were applicable for plant-based or organic food production, together with membranes that were actually operating in industrial conditions, like, for example, high temperature. During the second phase, then we do like an evaluation of individual performance of the membranes identified in the market. We evaluate a total of 5 ultrafiltration membranes, 3 nanofiltration membranes, and then we select a product representative for Agrana, which was the dextro 40 syrup. During this phase, we also evaluate different operating parameters, different temperatures, pressures, and feed concentrations to evaluate the performance of the membranes. Then we do a sequential analysis. We combine the membranes selected during the single screening to evaluate the benefits behind the multi-stage processes. So for that, we evaluate 9 configurations with ultrafiltration and nanofiltration using the same setup and with the operating parameters selected in the previous phase. Specifically, of course, for H membrane. Then, after the evaluation of the multi-stage, we combine them with the activated carbon in order to evaluate the benefits behind the ultrafiltration and nanofiltration pretreatment. For that, we use a powder activated carbon that is actually already used in the industry with different dosage concentrations, and also using the setup generated during the single screening, during the multi-stage, and then the operating parameters optimal for the activated carbon. And finally, we did an additional ultrafiltration long-term experiment to evaluate the changes in flux and the falling behavior, but also the cleaning in place procedure for the ultrafiltration membrane. For that, we do some tests over 30 hours of operation with the representative product. And in this case, we use, In this case, we use no batch mode processes, but a continuous processes with, of course, continuous sampling on the experiments. Yeah, so for a little bit of context, so the starch hydrolysases were produced with hydrolysis by agricultural crops such as corn, wheat, and potato. And the most common in the industry is the enzymatic hydrolysis, which is divided in different stages, like thermal liquefaction, then enzymatic liquefaction and saccharification, and then after the saccharification, as I mentioned, purification, but also concentration of the product, which is important for the stabilization of the starch hydrolysates. So during the enzymatic hydrolysis, we of course produce very different impurities, which are inorganic ions, proteins, color, amino acids, that can also interact between them and react, leading to a more color formation and also product stabilization. So one of the reactions happening there is the Maillard reactions, which are a complex series of chemical reactions between amino groups and reducing sugars, which are influenced by different factors like lower temperature behind 100 Celsius degrees, raw material, pH, and impurities residues. So for sure, the impurities are important and influencing in the color formation, and that's why it are very important to remove it. So the pigments generated during the Maillard reactions are called melanoidins, which we don't have a specific structure identified, and is a difficult molecular to insulate, I would say, or to quantify. But in the literature, we identify that this pigment is anionic, which has a negative charge, a brown polymeric substance with different quantities of nitrogen, but also mainly high molecular weight melanoidins. However, as we can see in the intermediate phases, we can also find low molecular weight melanoidins, which is a little bit challenging for our project. So membrane technologies, as we already mentioned, is gaining attention for sustainable alternatives and conventional clarification and purification methods. So we can find it in different types like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis, which are the pressure-driven membrane processes. And different factors, of course, affect them, like material, molecular weight, and operating parameters. So why membranes? Why we select membranes? Because it has different advantage in comparison with conventional methods, like for example, lower energy consumption, operation without chemical additives, mill process conditions, and etc. So it is for sure a good alternative for the ion exchange technologies and for the organic production. So for our experiments, we use mainly a lab-scale closed-flow filtration unit in our institute with a flat sheet membrane with a 2-liter tank and with a temperature control. Depending on the experiment, so in the first experiment, we do short batch operation, but during the long-term processing, we use continuous operation where the retentate and the permeate was recycled to the feed tank in order to keep a continuous process, which is beneficial to have a better strategy for the large industrial application. So, as I already mentioned, membrane screening was evaluated with different membranes, but also different membranes with different molecular weight cutoff and materials, different conditions, and we mainly evaluate different depending variables like permeate flux, rejection coefficient, and color removal. And from that, we select the best membranes tested, but also the best operating conditions. After that, we wanted to make sure that these membranes behave constantly, and we did some replicate experiments to confirm their performance and then have the main conclusions. So based on the membrane screening and previous investigations, we know that the effective membrane will be like high permeate flux, efficient color removal, minimal sugar loss, and low fouling propensity. So, however, like there was like a limited color removal, approximately to 53%. Rejection with the highest value with the 20 kilodalton membrane, which suggests that the color compounds present in the product comprise a broad molecular weight distribution with a significant fraction of also low molecular weight pigments. So here in the table, I cannot show all the results, but in the table 1, we have a summary of the membrane screening results when we use a semi-quantitative KPI to select the membrane that the best membrane performance. After that, we have a tight ultrafiltration membrane of 5 kilodalton, then a low ultrafiltration membrane, and then a nanofiltration membrane selected. During the replicates, we confirmed their performance, and then we observed that the ultrafiltration stages provide a partial decolorization with 18% color removal during loose ultrafiltration, and then 32% of color removal during tight ultrafiltration. However, the nanofiltration step didn't contribute further to the decolorization, as we can observe. For the nanofiltration, the product is in the permeate and not in the retentate. But we observed like a really good contribution on the concentration of the product to 85%, and additional benefits on the purification of other compounds. So that's why we also select this nanofiltration membrane. So our idea was combine these 3 membranes in order to make a better optimization of the product or the process. And then we do an additional test of carbohydrate profiling and additional size exclusion chromatography to evaluate the molecular weight distribution before and after the treatment. This test was very important to confirm that after the treatment, there is not any significant change on the composition of the final product beyond the intended removal of the impurities. So finally, the conclusions for this step is that no single membrane can simultaneously remove sugar, maximize sugar recovery, color removal, and purification. So we need to integrate the ultrafiltration and nanofiltration in order to improve the process. So the next step was focus on the multi-stage trials, as I already mentioned, with the selected conditions. So so here I am going to talk about the multi-stage, but also the combination with activated carbon. For this, we also use the batch cross-flow filtration system I already mentioned before, using 4 different polymeric membranes for the multi-stage trials. And then we focus on the multi-stage and the single screening in combination with the activated carbon. Of course, this process also have additional benefits and additional focus, like, for example, the recovery of the product from and the recovery of water from the retentates or from the permeate side. So yeah. So we test different 9 configurations with single stages, 3 stages, 2 stages, and also diafiltration. And after the configurations, we use the product to treat it and evaluate the activated carbon. So from these experiments, we select 2-stage sequencing configuration, which had the best performance in terms of color removal during the tight ultrafiltration, and then during the tight nanofiltration, the benefits in terms of sugar concentration, but also in terms of other impurities removal. Very important also for the next stage, like, for example, evaporation, which could save a lot of energy in the process. So from this stage, also we can observe like a reducing of activated carbon demand of up to 74%, and maintaining also the color specification that we want for the product. However, it's important to mention that a dedicated techno-economic environmental analysis is still required to quantify and confirm the benefits behind that of the proposal configuration. During this trial, we also identified that one of the main challenges are the sugar retention in the membrane side streams, which could have a principal limitation for the industrial implementation. However, I recommend as a future research to dedicate this on the recovery and valorization strategies, like, for example, retentate recycling, modified diafiltration schemes, and alternative diafiltration utilization pathways. But also it's important to mention that this is just the beginning, and the process needs to have a better analysis and process design, considering different advanced configurations like parallel design, in-series, and feed-free design, or maybe a combination of them in order to improve the efficiency. Another thing that we identified during this is that there is a limited knowledge on the membrane lifetime under realistic operating condition, and that's why we go to the next stage, which was the long-term performance of tight ultrafiltration membrane. Why we select this membrane? Because it was the more representative of our trials in terms of the colorization. And we evaluated during a trial of 32 hours of a continued operation. During this time, we confirmed that there is a mechanical and thermal stability under industrially relevant conditions. But with, of course, like an expected gradual decline of total sugar and water fluxes, indicating a progressive falling dominated probably by the carbohydrate compounds or organic compounds. Falling, of course, partially lead to a partial pore narrowing and the formation of a secondary layer, increasing the retention of larger carbohydrates. So here we can see the rejections. So here we can see the rejections of the membrane. Sorry, you can see. Hello?
Yes, we can see.
Okay. So we can see the rejection of the color, sugars, and salts. And then we can see that that sugar rejection especially increase over time, probably for the organic fouling, and the salt rejection remain negative through the experiment, indicating that the salt probably has a higher concentration in the permeate than in the feed. Color rejection in the other side doesn't have a linear behavior, which was a little bit strange, but these indicate, of course, an interaction of the membrane solute of the membrane and the solute, by also a change of feed composition, where we can see in the second graph where the color intensity on the feed and in the retentate is increasing in the second, third, and fourth trial, which indicate that is a change on the product during the processing, indicating a falling color formation in the process. However, as we can see in the permeate, which is the product during the ultrafiltration membrane, we see a consistent color intensity of our product. Finally, we also did a sugar, a specific rejection analysis, where we check the ions present in the product, but also the individual carbohydrates. With that, we confirmed the rejection of sugars, the increased rejection of sugars over time, especially with the high molecular weight sugars like the DP4+. Then the salts transport, as expected, is a little bit more dynamic, but anyways, the divalent ions showed a more stable rejection and a little bit higher than the monovalent ions, combining, reflecting a combined aesthetic and electrostatic effects, influenced, of course, by fouling and probably concentration polarization. So during this test, we also did a cleaning in place performance, where we evaluate alkaline and acid cleaning during the different 4 cycles. And during this time, we confirmed that alkaline cleaning it was more effective for the flux recovery radius up to 80%, confirming again that the predominance falling of the system, it was organic. During the acid cleaning, we have a limited additional benefit, which indicate that there is a minor role on the inorganic scaling. We also observe a reduction of flux recovery through the cycle. So this is the cycles, around 20% through the experiment, indicating that the importance of optimize the cleaning frequency and the membrane lifetime management. So finally, the main conclusions of my project was a membrane-based purification is possible and is viable as a sustainable alternative for the process. However, a single membrane stage is insufficient to achieve simultaneous decolorization and further purification of the product. The optimized ultrafiltration and nanofiltration configuration with activated carbon improved efficiency, but also reduced the activated carbon consumption. And finally, the long-term filtration test confirmed that it could be a very stable operation and with an effective cleaning procedure, and that the organic folding remains the main operational limitation. As I already mentioned, techno-economic and life cycle assessments are important in this case to confirm the additional benefits. Sugar losses important for the recovery of the and valorization of the product. Cleaning in place procedures improvements, especially on the predictive monitoring and nowadays indicators that can provide soon a strategy for the membrane. And finally, pilot scales trials are very important in this case to support the digital monitoring and model-based process control required for a more to translate the laboratory results to a more industrial process. Finally, thank you so much for everything. I hope it's not a lot for my presentation, and if you have any questions, I'm happy to answer.
Thank you. Thank you so much, Camila, for this very interesting presentation, and congratulations for this amazing work. Is there any questions from the audience? I can't see anything. Mm-hmm. Yeah, one. Okay.
Who is it? Priyanka.
Priyanka. Can you unmute yourself?
Yeah, now I can.
Yes, okay.
Until now I wasn't.
Thank you.
Yeah, it's a very nice talk, Camelia. I just wanted to ask in your conclusion slide that you mentioned about some optimization, if you like predictive steps for for example, like predictive monitoring. What do you mean by that one? Is it like the design of or can you please explain?
Yeah, I think I will say like to use all these data sets of fluxes and behavior in order to create first a modeling of the process specifically for this process. I will say, and then to with the time predict what could happen if you change something on the process. That's what I mean with predictive monitoring, but especially for the cleaning in place procedure, having like some sensors to know what is the flux at the moment, what is the transpressure membrane at the moment, and the color trends in order to predict what to do at the right time. No.
Yeah. So I mean. You mean like choosing the right procedure even before going for the experiment based on what you have, what you get, right?
No, with predictive monitoring, I would say for the process itself in the real scale, because you always face these problems on the industrial scale when you can, when you can react fast. No, so if I know that the flux is wrong, if the flux is not going well, so I can react fast and maybe apply like a cleaning procedure before the membrane is damaged or the process is
okay. So this is
wrong.
the
Yeah.
Okay. Thank you.
No problem. Thank you so much. Thank you for the question and the answer. And thank you, Camilla. I know that there were many challenges in doing this project. It was really comprehensive. And I know that you were successful in publishing in very high quality journals. Best wishes for your future career. And I think we need to go and move on to the next speaker.
Thank you, Nela.
You're welcome.
See you soon.
See you. Yeah, and good that the next speaker is you. Dr. Christoph Hofer, you can start definitely, and you will present recent results on membrane performance for water treatment applications. We are listening.
Thank you.
Yeah.
So you should see my screen. Is that right? All right.
Yes, I can see.
Okay, so today I have the pleasure to also present a little of a previous project we were working on, which deals with hollow fiber membranes. And here we were looking at polyethylene hollow fiber membranes, and we were modifying them with electron beams with one of our project partners. And then we checked the performance for ammonia removal as a membrane contactor in a vacuum membrane distillation setup. So why is this important? First of all, nitrogen is and will still be a huge topic. If we look at the nitrogen fluxes simply in the European Union, in the EU 27, we see that only a very small part of that is natural fluxes, and most of the fluxes of nitrogen are introduced by human activity. And if you look at everything which is displayed in yellow, most of the fluxes are unintentional fluxes. So we have a lot of losses. And on the other hand, if we look at the current situation of the production of ammonia is contributing to about 2% of the global energy production. So the costs are very high for the production, the losses are very high. So what does it result in terms of circular economy or in energy efficient use of the resources? It basically means that we should focus a little bit more on recovery of nitrogen. And here I just plotted a little example for what ammonia can be used. So very often it's used in for agriculture, but it can be also used for energy production, and it also has expanded uses. Nowadays it's in discussion for fuel cells, also for direct combustion and usage in turbines, and so on and so forth. And also this may ultimately remove the CO2 emissions on a global scale. And especially the anthropogenic ammonia usage, if you look in the pure numbers, around 80% is currently used in agriculture. So here we have the highest potential of reusing ammonia, and the project we were having and working on tried to address partly these issues. So what does it mean if you want to recover ammonia from a wastewater? Basically, there is different technologies around. However, the overall stream is always the same. You have an ammonia-rich wastewater stream. You need any type of recovery technology, and then you need a reuse strategy, and then you can reuse it again in whatever field, industry, agriculture, or energy. Since we are working a lot on the membrane-based recovery technologies here at AEE in our working group, we had especially a look on membrane distillation as potential technology, and especially in the membrane distillation for ammonia recovery, very often the membranes applied are based on very hydrophobic PTFE membrane contactors. And the project here aimed on investigating the same type of removal and recovery technology based on polyethylene-based membranes. So vacuum membrane distillation in a nutshell, what does it do? So on the one hand, we have a feed circle where we pump the water we want to treat in a circle. Then we bring it in contact with our membrane, and on the other side, we evacuate the resulting gases by a vacuum pump or vacuum setup, and then we are starting to condense the gases in any type of setup to liquefy the gas again and recover the product. However, since this process is driven by the water vapor pressure difference between hot feed side and the vacuum side, ammonia in the gaseous phase is similarly affected as the water vapor. And so one of the problems with vacuum membrane distillation for ammonia recovery is that we need to maximize the ammonia flux in order to keep the H2O flux the lowest. And this is challenging since the membranes are usually unspecific. So the target is in any case to increase this ratio between ammonia and water in the gas stream. And this is exactly what we used as an indicator for the performance assessment, which I will show in the next slides. So target here in this project, after running over the main driving factors of why we are doing it, this is actually the method we applied. So we used a hollow fiber membrane bundle made from polyethylene hollow fibers. We ran it through an electron beam grafting technology, which was done by our colleagues from Institute of Surface Modification in Leipzig in Germany. And after the modification, using different monomers, which we grafted onto the membranes, we tested the membranes for the performance. And on the bottom right, you can see what we wanted to achieve. So the idea here was actually to make a hydrophobic membrane partly hydrophilic and to basically trap the water and the vapor phase in the surface containing area in order to increase the ammonia transport. This was the concept. So how did it turn out? So we tested the membranes after the modification here at IEA INTEC in our laboratory setup. And we tested the different conditions and different modified membranes. So to give you a short overview, what we did is we produced some artificial reference solutions of ammonia at 1 and 3 grams per liter. This is a range which is a typical range for wastewater concentrations or waters coming from biorefineries. And we prepared receiving solution of sulfuric acid to trap the ammonia and transform it back to its acidic state in an ammonium sulfate solution. We did this at 2 different pH variations, so we tried to keep the pH as low as possible. We did it at 8.5 and 9.5, and we did it at a moderate temperature of 45 degrees and a very typical MD temperature of 60 degrees. We tested different variations of hollow fiber membranes against a PTFE reference membrane. So on the one hand, we have the PTFE reference, which is a commercially available membrane used for ammonia recovery. We used the PE reference membrane in the pristine configuration. And then we used 3 different modifications, which turned out to be the most promising one in the research project. The one is PEG, polyether glycol modified one. The other one, which is basically trying this approach with having a slightly hydrophilic part of the membrane surface. And then we also tried 2 different configurations with one SPMA and DMEA modified membrane, which the one is more producing an anionic charge or negative charge, and the other one is more a cationic positive charge. So this was the configuration we tested. And after several sets of experiments and producing a lot of lab data, we found that there is 2 or 3 which are really interesting configurations. So if we now look on the graph in the middle, you see the total flux, total membrane flux plotted over the cm value of ammonia. And so in a nutshell, the more left and the more high, the better, because this would mean that the concentration would be the highest, or the mass transfer for the ammonia would be the highest in relation to the water transport. And we found that some of them are a little bit sticking out. Also, when plotted against the productivity, this can be displayed a little bit different, and some others popped out to be quite interesting. And if we look at it in a little bit more detail, it was quite evident that the polyethyl glycol was a quite promising candidate of the modified membranes. To look into a little bit more detail. And if we look now on some of the results at pH 8.5 and 1 gram per liter, we already saw that in the selectivity, which is essentially just the ratio of ammonia transport divided by the total transport, we see that with the polyethyl glycol at lower temperatures, at around 45 degrees, there is a distinct enhancement of this ratio. So compared to the PE reference, we already saw there was some improvement. However, when we look at the polyethylene membranes at the higher temperature, at 60 degrees, this was not really evident anymore. So we made a little bit a larger set of experiments where we then included all of the candidates. And looking at the big picture here, what we can see is that we could justify also at pH 9.5 pretty much the same set of results. However, even here, the PE reference membrane performed relatively well at 45 degrees, similar to the PEG modified and also to the cationic form of the modified membrane, whereas the variation for the PTFE was relatively large at the low temperature, similar to the SPMA. On the other hand, at higher temperature, at 60 degrees, this turned a little bit around, and we saw that the reference PE membrane and the PEG performed much less, and showed higher variation. We repeated the same thing at 3 grams per liter and found a little bit similar picture. So also at higher feed concentrations, of course, we get some higher selectivity ratios of around 3% of pure ammonia in the gas stream. And we see a similar trend between high and low feed temperature. So to sum up some of the findings from this project, first of all, what we can say, and I think this is really nice, is that the polyethylene hollow fibers, they can remove ammonia, and we could show that in the VMD setup. This was pretty good. The PTFE membrane, which is currently, I would say, in this application field, the industry standard, generally perform better at the higher temperature, while the PE membranes were competitive to the PTFE at the lower temperature, which is actually a really great result, because we could see this the first time, that at 45 degrees, PE and PTFE perform relatively similar. In some points, we were even superior than the PTFE. But since that is the first data set, I would not nail this down in the coffin at the moment. One thing we have to discuss here is the surface properties itself, since the E-beam modification does not only have an influence in grafting the new molecule on, it also changes the crystal structure of the polyethylenes, so it gets more crystallized to some extent, and this can also change a little bit the surface properties. We couldn't investigate this in more detail, but this is definitely a fact which should be looked into a little bit more. And on the other hand, in our data set, which I showed now, it's not fully comparable, because the contact angle for the PTFE membrane was very large, where around 130 degrees, whereas for the PE membrane, we were almost at the barrier to being hydrophobic. So we were around 90, 91. Yeah, so it was actually very conservative, that the PE membrane itself was not a very good performer for this type of experiment, still performed very well. So bottom line at the end of what we found in this first project, the electron beam functionalization shows a very high potential for ammonia recovery and for functionalizing membranes for this application. And like polypropylene membranes, polyethylene membranes are also a promising PFAS-free alternative for this type of applications. And with this, I'm actually at the end of my talk for today, and I would like to thank all of my colleagues at the AEE, so the VPT team, and also all of the people in the Solpol 6 team.
Thank you. Thank you so much, Christoph. It was a very good presentation and clear and informative slides, and very interesting topic related to ammonia recovery. And is there any question from the audience? We have time for some short questions. If anybody has a question, please raise your hands. Or maybe I can ask one question about, I couldn't understand the reason for considering this pH range for between 8.5 and 9.5.
Yeah, I can shortly comment on that. So for the ammonia equilibrium, the pKa is around 9.2 at 20 degrees. So at 9.2, you have around 50% pure ammonia or free ammonia and 50% ammonium in your feed solution. If you are lower than that, you always have to induce a gradient by removing, and usually the removal rate is much lower. On the other hand, for this type of application in MD, usually the costs for adjusting the pH are the highest. So in an economic sense of view, you would not like to adjust the pH higher than required for facilitating the process. So 8.5 to 9.5 is a good range to assess actually if the process is still working, even though you are below the pKa or very close to the pKa.
Yeah, thank you. And if there is not any question from the audience.
I would say we keep the time plan as it is. And we have to make a break now and then come back at 2:30.
Christoph, this is Priyanka. I have a quick question. During your presentation, I couldn't ask that one, but I thought it could be good to know what is the progress of your hollow fiber membranes and how far you can, in what scale you can produce them. So, for example, if we try to do something, how can we reach out to you if we need something, and what is the scale of your production? So,
Yeah, sure. I can quickly comment on that. So in the research project phase, we are working together with the Institute of Surface Modification in Germany, who actually is doing the surface modification. And the membrane is produced by an Austrian membrane producing company. So AEE is solely involved in the testing, and we just do the performance assessment. Related to the scale of the membranes we use now, we are in the range of around 0.1 to 0.5 square meters. So very small lab test setups. However, the technology itself for the surface modification, they can already modify roll to roll for flat sheet membrane. So also on large scale, the modification itself would be feasible. But this is all needs further development. So currently we have a low TRL. We are in the lab scale, and the membranes we produced or had produced in the project now is still in the research state.
Okay. But like for example, the flat sheet roll to rail is doable in a large scale.
The technology itself is capable of doing that, yes. And it's currently already done, I think, for PP membranes and also PTFE and related. For PE, the field is still relatively new. So that's why this project was put together to work on the polyolefin membranes.
It's very good to know, because we also have some developments regarding the membrane distillation, and sometimes it's a bit hard to find the right membrane. So it's very good information and good to know that we have something else. Thanks.
You can just reach out to me after the workshop, indeed. And then we can get in contact, no problem. Yeah.
Perfect. Thank you so much.
Okay, so thank you so much for your question and answer. I'm again Natasha Sian, and I will be chairing this PhD pitch session. There is a little bit change. I'm doing this instead of Bettina, and then she will do the next one. Okay, so in this section, we will hear a series of short presentations from PhD students, and they are presenting their latest work. And each presenter have, I think, a few minutes, 7 minutes, so we will keep transitions quick. So let's begin with the first speaker that we have, Mia Jurkovic from the University of Twente, the Netherlands, and they will talk about solvent-resistant membranes. You can start.
Hello, everyone. Can you hear me?
Yes.
Yes, thank you for invitation and organizing this event. So now I will share my presentation. Okay. Can you see the presentation?
Yes. Yes, we can see.
Okay. So now I will briefly explain my project. So I'm working on solvent-induced effects in PDADMAC PSS membranes, and the goal is to go towards solvent-resistant nanofiltration membranes for biorefineries. So my project is part of MEMFAST doctoral network, and my individual aim is actually to fabricate material or membrane to enable effective treatment of complex streams containing organic solvents such as ethanol, methanol, isopropanol, and so on. So for that purpose, I'm using naturally stable building blocks, and these are polyelectrolytes to build actually advanced functional membranes. So for that purpose, I'm building two systems. One of them is polyelectrolyte complex membranes, so-called celloplastics, and the other one is polyelectrolyte multilayer membrane. So first one, celloplastics, is freestanding membrane, while multilayer is actually film or on a porous support, and I'm working with flat sheet membranes. So first I will start with celloplastic membranes. So celloplastic membranes are made in a way that we mix two polyelectrolyte solutions. We get a complex, and then we hot press it under high temperature and pressure, and we get this plastic looking like material, which is actually acting as ion exchange membrane. So with this material, I performed some experiments. So one of them was solvent uptake that I measured only by weighing dry and wet mass of material after immersion in a solvent mixture. And the other experiment was quantification of ethanol content in the membrane. So this was done for the first time for this kind of membranes with proton NMR method, and this was possible because celloplastic membranes are can be dissolved in a high concentration of salt. So from these results, we can see that with increasing the ethanol in the bulk, solvent uptake is decreasing, which means that swelling is lower. And also we can see that even when we have a high swelling, the content of ethanol in the membrane is low. So it means that there is some kind of preference by membrane towards water or some kind of, let's say, selectivity. So with this conclusion, I wanted to proceed with my real system and to see effects in the real filtration. So for that, I prepared this polyelectrolyte multi-layer membrane using a layer-by-layer method. So I was deep coating the pan support and first immersing in PDADMAC as polycation and then PSS as my polyanion to build a multi-layer. And in that way, I built a multi-layer of 13.5 bilayers. And with that membrane, I tested first permeability in different feeds containing 0, 20, and 40% of ethanol to see actually the effect of ethanol on this polyelectrolyte membrane. So here I also corrected this permeability for viscosity to actually distinguish this viscosity effect from the change that is happening in the membrane. And we can see that with increasing ethanol content in the mixture, permeability is decreasing. And following on that, I also measured magnesium chloride retention. So here you can see with these gray triangles, which is describing 40% ethanol feed, we have the lowest retention of salt, which means that with increasing the ethanol in the feed, both permeability and retention are decreasing. And also I checked selectivity for this kind of system, and there was no observed selectivity between water and ethanol in this situation, which was checked by refractive index measurement. So these experiments are still ongoing, so more results and conclusions will follow in the future, but for now it is visible that membrane is changing and there is lower swelling, but also lower Donan and weaker Donan exclusion while concentration of ethanol is increasing. Thank you for your attention, and I'm happy to hear the questions.
Thank you so much. Thank you so much for speaking in your time schedule. And yeah, very interesting work, and definitely these results are part of a bigger project, but very interesting. If there is any question from audience.
Thank you.
If there isn't any question, maybe we can move on to the next speaker. Thank you so much.
Thank you
for your contribution in this webinar. Okay, so our next speaker is Sissi Poo from University of Calabria, Italy, and she will talk about functionalized cellulose membranes.
Thank you. Okay, let me see. A moment. Thank you for your introduction. So now you can see my presentation.
Yes, we can see.
Right.
But
Okay.
Still not in the slideshow.
Now it's okay?
I think you need to share the other screen.
How to transfer it to... Okay, I will try to stop sharing and share this screen. Okay, one moment. Okay, now it's okay, I think.
Yes, thank you.
Okay, thank you so much. Thank you for your introduction and good afternoon, everyone. Today, I would like to talk about the cellulose-based membranes functionized with magnetic responsive nanoparticles to enhance the protein rejection. As we know, during high-valued protein sorting process by the membrane technology, one of the challenges about the concentration gradient that formed on the surface of the membrane that will result in decreased flux and increased energy consumption and so on. Then go back to the membrane materials that we choose the hydrophilic regenerated cellulose membrane with the 30 kilodalton molecular size. That one is with very good intrinsic no protein absorption, but also commonly applied in a factory. But in our preliminary experiment, we found based on the BSA rejection with this membrane, it's quite lower, and will also decrease with the heavier foaming on the surface of the membrane. And even though the solution BSA solution flux will improve the anodes by increasing the axial flow rate of the solution, but there is some papers indicated that with the higher shear stress will result in deactivation of the protons, so it's not good for the proton sorting. And so for us, we would like to do the functionalization of the membrane with the magnetic nanoparticles that can produce the micromixing on the surface of the membrane to resolve the problem. Okay, so firstly, it's about the membranes fabrication. We through the stepwise chemical modification, and for the last steps regarding the immobilization of the single layer of the particles, we do the immobilization by the low pressure filtration for 2 hours. This is the functionized membranes picture, and we found that functionized membrane has a very low absorption for the BSA protein, and this one didn't compromise the intrinsic no absorption of the plastic membrane. Then it's about the stability of the membranes. We've found for the plastic membrane and the functionized membrane, both of them have achieved the full pure water flux recovery. And after 3 cycles BSA filtration, we saw the still 100% recovery. It showed a good stability for both membrane. And then it's about the protein ultrafiltration flux that we did in concentration mode with the low shear stress steering in the solution with the different concentration of the 0.1 gram per liter of the BSA mode solution and the 0.5 on the different pressure. Based on the result, we found for the flux of the functionized membrane is very close to the plastic membrane. However, regarding the rejection of the BSA throughout the concentration process, we found for the functionized membrane, it still keep a high unstable BSA rejection. However, for the plastic membrane, the BSA rejection showed a rejection drift. It means it will decrease with the increasing concentration in the retentive sites. And with the higher concentration of the BSA as a phase solution, we found the functionized membrane can keep a very stable and good rejection above 95%, even though the highest concentration of the BSA reached up to 3 grams per liter. Yes. So to have a conclusion, we know with the optimized chemical modification, we can get the good uniform single layer attachment of the particles, and without compromising the flux of the plastic membrane, maintain its structural integrity. And compared with the plastic membrane, the functionalized membrane achieved a linear, complete, and stable rejection, even under prolonged operation. These encouraging results provides a robust strategy to transform commercial membranes into smart, responsive platforms for the high purity protein protein purification and concentration. Yes, that's all. Thank you.
Thank you so much for your presentation. Yeah, thank you so much. And if there is any question from the audience side, please share it with us. Okay, Christoph Hopper, you have a question?
Okay.
Yes,
please.
Yes, I would be interested in, you mentioned the rejection rate of 95%, which you
yes, about the
so
rejection. Yes.
Was this for mono and divalent ions?
Sorry?
Was this for mono and divalent ions, or how was it calculated? Because sometimes this is a little bit different.
Oh, you mean the rejection? I calculate the rejection of the BSA. Yeah, in the concentration mode, because we cannot, in the concentration mode, I calculate the rejection by the, how to say, by the initial phase, the solution concentration minus the permit concentration of the BSA.
Mm-hmm. Then
divided by the initial concentration, because in the concentration mode we cannot take the solution from the seal, so we use the initial concentration anyway. Because at like this, at these points, even though we take the initial concentration, it's much lower than the practical concentration in the written site.
Mm-hmm.
Yes, at this time it's around 3 grams per liter of the protein of the BSA concentration. It means we still get about 95% of the rejection. It means the concentrating property is very good of the functionalized membrane.
Great, thank you. Thanks.
Hope it's helpful.
Thank you so much. Yeah, and we have one question in the chat. Atif Afuz has asked, have you checked the leaching of iron?
The irons, we cannot separate it, and in a solution we fix the iron concentration, because we prepared the protein solution in the phosphate buffer with 50 millimolar and fixed the pH at 7. So, yeah. 1 moment. I want to see that. Okay. Yes.
Okay.
Yeah.
So, yeah. If there is not any question,
thank you.
You're welcome. Thank you for your contribution. Okay, so we will listen to Abdul Rahim from Karunia University, India, who will talk about comparison of ion exchange bits for wastewater treatment.
Okay, ma'am. Good evening, honored all present here. Myself, Abdul Rahim J. I'm also working Senior Research Fellowship and now I am doing PhD in Water Institute, Karun University, Coimbatore, India. My topic is comparative evaluation of performance of anion and cation membranes and beads in wastewater treatment. This is my contents. Study overview of my project is PVA membrane, polyvinyl alcohol membranes, and activated charcoal beads were compared for wastewater treatment. Membranes had better ion exchange while beads showed stronger absorption capacity. I choose this topic to explore simple, affordable, and effective treatment materials. My main objective is to fabricate and study the characterization of anion and cation exchange membranes and beads for desalination process. Comparison. My sub-objective is the fabrication of anion and cation beads and membranes using PVA, including PEG polymers, polyethylene glycol, for increasing the porosity, to evaluate the performance of anion and cation beads and membranes, and to compare it with commercial membrane. I have bought the commercial membrane also. Analyzing the property and characterization of test is done for each membranes and beads. Then testing the membranes by using NaCl solution, synthetical, and checking the result reduction in TDS if occurred. Checking whether the deionization is achieved or not. This is my methodology. Fabrication of membranes and beads, characterization test, experimental setup, and finally result. Both beads and membranes are tested in TDS reduction is mainly monitored in desalination process. Anionic is prepared using PA, polyethylene amine group, and cationic by adding SSA, sulfosuccinic acid. Both cross-linking is done by glutaraldehyde. Beads prepared by 30 grams of PVA and 1 gram of PEG polymer dissolved in 180 ml of DMF solvent, because that is insoluble in soluble in water. Properties of materials: PVA, good film forming ability for mechanical strength and high water absorption. I choose PEG polyethylene glycol for improving flexibility and porosity of membranes, and sodium alginate enhancing the cell formation and bead stability. Activated charcoal adding in the bead high absorption capacity, increasing pollutant removal compared to membranes. PEI for anionic and SSA for cationic. Glutaraldehyde for cross-linking stability. This is the chemical structure of my polymers. Cationic membranes, PVA with GA cationic functional group. This is the chemical formation of that. And second one is anionic membrane, PVA with the GA anionic functional group. Overall structure that cross-linked. Fabrication of beads. This is I prepared beads. This is the procedure. Dissolved 10 grams of PVA in 250 ml distilled water and added 5 grams of PEG and sodium alginate. The final mixture forms the base solution for bead preparation. Swelling test comparison. Anion and cation PVA with the mesh, without mesh, and PVA including size and swelling behavior. This is the formula of the I took in commercial membrane comparison. This is water uptake test comparison. Anion exchange membrane 48.27%, cation exchange membrane 51.61%. Ion exchange capacity, I took 0.1 normality of NaOH for anion and 0.1 normality of HCl for cation respectively. IEC is main exchange capacity in comparison of membranes and beads. Ion exchange capacity for commercial membrane comparison. PVA cation exchange membrane, PVA anion exchange membrane. Ion exchange capacity in this hydrogel means bead. I compared membrane to bead 1.33% and anion exchange beads is 0.632%. This is the TDS removal results compared to PVA anion exchange membranes and activated charcoal beads. Compared to membranes with beads, gradual decrease in the TDS removal. This approaches good desalination process. This is, I took the raw textile wastewater, no, not textile wastewater before RO treatment. That has 6,700 ppm TDS. After the adsorption column, I took the anion exchange bead in 10 cm, 100 grams, and below cation exchange beads 100 grams. That height is 10 cm. So I took the process. After 10 minutes, TDS become reduced 6,700 to from 6,700 to 3,000 ppm within 10 minutes. pH also boost up. The pH increased 3.8 from 3.8 to 4.4. That leads to anion exchange group activated. This is the graph of pH and TDS level. Both. I also regenerate the anion and the cation exchange beads. Best tested beads tested in NaCl solution. These are the results. I also calculated hardness and chlorides. This is NaCl solution. This is also different approaches of chromium wastewater, electroplating wastewater, and different types of weighing 10 grams, 5 grams. What is the difference? These are the batch study. This is my interpretation. Wastewater initially had high TDS 6,700 ppm and acidic pH 3.8, nearly 3.8. Regenerated beads cationic. This is the regeneration of the process. Cationic 4% HCl and anionic 4% MnOH worked. And sharp TDS drop to 3,000 ppm at 10 minutes. Active sites fresh and highly efficient. After 10 minutes, TDS increased again 5,100 ppm at 30 ppm. 30 minutes. 6,700 ppm at 70 minutes, 1 or 10 minutes due to breakthrough. Beads became rapidly saturated because of heavy salt load in the real wastewater. pH dropped from 3.8 to 3.0 finally due to hydrogen release release from cationic beads. Initially done from anionic beads and finally cationic beads also activated. Column maintained acidity instead of neutralizing it. Effective only for first 10 minutes. Performance decreases after saturation. Regeneration required every 50 to 60 minutes to restore the ion exchange efficiency. Conclusion: the regenerated ion exchange beads faster and sharper TDS removal. Beads are provided greater surface contact with wastewater, allowing rapid ion exchange and quicker responses. The flexibility in regeneration of beads is make them easier to restore and reuse. This is also the sustainability. Unlike membranes, beads do not face issues like fouling, scaling, or pressure drop, making them more practical for handling complex in industrial wastewater. Beads can mixed, packed, and fluidized, giving more operational flexibility than membranes. Overall, the study indicates beads are more effective than membranes. for rapid ion removal, easier regeneration, and better adaptability, making them the superior option for treating highly saline industrial wastewater, initial stages, and repeated cycles. Thanking you. Save the water, save the future.
Thank you so much for your presentation. We have already one question in the chat, and if anybody has a question, please raise your hand. So I will read the question from Atif. In the synthesis procedure, how did you control the gelation during cross-linking with bilateraldehyde? Is there any method to optimize the swelling property? Abdurrahim, could you please answer to this question?
Yes, ma'am. Where is the question?
Yes. In the synthesis procedure, how did you control the gelation during cross-linking with bilateraldehyde?
How do you polymeric membranes withstand the high temperature of the? I did the in the initial. It's that only
you can
batch
see the
studies
question
are.
also in the chat.
Yes, ma'am. I can see how do the polymeric membranes withstand the high temperature of craft liquor? I will study the high temperature, ma'am. I've not it done nowadays. I need to answer this question in practically, ma'am. Not it done in high temperature of the craft. So I couldn't.
Increasing the temperature can control the gelation, you mean?
Yes, ma'am. Yes.
At what temperature did you work, and did you compare the temperature effects?
Not it compared in the temperature, ma'am. I need to study that. Now, now a time I just compared to membrane. How beads are better than membrane, because membrane have fouling and needs to replacement. But compared to beads, beads can easily easily regenerating that using 4% minimum level and again usage of beads.
I think your focus was on the application comparison of these two, not on the synthesis. I don't know if Atif got your answer or not. If you still have any further question or any other people from audience. If you have question, please share. If not, the answer is not satisfactory. So maybe this is something that you can
sorry for that.
Think about that in your synthesis and experimental part. Thank you so much. Okay. Do we have any other questions? Okay, so I think we can finish this session.
Okay, I think once it's sharp 15:45, we can start into the next session. I'm very happy that I'm able to chair this session this afternoon. And my name is Bettina Mustislavic. I'm working at IEA INTEC as a non-university researcher, and myself being a process engineer. And at IEA INTEC, I'm leading the group Water and Process Technologies, a research group focusing on energy efficient technologies in circular economy. This session will be focused on membrane distillation now, and I'm very happy that I can announce Professor Cesna Christiansen as our first speaker. Cesna is a professor at Aalborg University at the Department of Chemistry and Bioscience. She has a very long research focus on membrane distillation and crystallization. And besides her really, I would say, over the year-long research and work in academia and teaching, she's also leading several European projects, national and international projects. So yeah, I think we have the expertise of membrane distillation with us now. And Cesna, we are very much looking forward to your talk.
Thank you, Bettina. Thank you. So I will just give a talk on membrane distillation and also membrane crystallization. The title is called Membrane Distillation in Biorefineries, Advancement and Prospective Role. I might not go so much into biorefineries, but I hope that you can see maybe the idea and the concept of membrane distillation and membrane crystallization. I know there has also been and will be other talks on membrane distillation, but I'm always open to discuss this more and also to collaborate. But now I will first have the presentation. So what we actually focus on in my research group at Aalborg University is more the industrial waste streams, but here biorefineries can also play an active role. So we look into different wastewater streams, for example, from the manufacturing and process industries. We also look into wastewaters from desalination processes like NF reverse osmosis brine. We focus on battery recycling, waste streams from mining sites, and also like salt lake brines, for example, from South America or geothermal waters. So this is where we normally implement membrane distillation and membrane crystallization. And the logic behind this is that it's a thermal driven process, but where we can concentrate the solution until we recover different minerals or different valuable products from the waste streams, and then at the same time recover pure water. So my research is mainly focused within this technology. So what is written here is that my research is mainly focused on the mineral contained streams, but there can also be like a perspective in using membrane distillation in biorefineries. So what is membrane distillation and coupled with membrane crystallization? So maybe you have heard about it, but it's a thermal process where we have a warm feed solution, and then we have a microporous hydrophobic membrane, and that means, and then we have a cold permeate stream. This is the most simple setup of membrane distillation, which is called direct contact membrane distillation, where we have a cold permeate stream, but it can also be vacuum or sweep gas or an air gap. So there can be different configurations, but this is the most simple one. So what happens? We have a temperature difference between the two sides, and then due to the hydrophobic membranes, the solvent will evaporate at the interface of the membrane, go through the membrane as vapor, and then being condensed on the other side of the membrane. So the normal solvent that we are working with in my research is water, where we have water, but it could be also different alcohols, for example. So we could use it for ethanol separation, for example. So it's a different process than the pressure-driven processes. So we can have a theoretical complete rejection of all non-volatile components. We also use relatively low temperatures between 30 to 70 degrees, normally depending on what kind of feed solution that we are using. So we have a quite broad temperature range, but at the at low temperatures compared to, for example, conventional distillation. And then we don't apply pressure as we do in the pressure-driven membrane processes. So that is also one of the advantages of membrane distillation. And due to the temperatures that we're using, we can use low-grade or waste heat or other alternative energy sources. So right now we're also working on how we can, for example, integrate membrane distillation with heat pumps. And then another advantage of this process is that it's not affected by concentration as much as in the pressure-driven membrane processes. So that means that we can actually use it as a membrane crystallizer. And in membrane crystallization, we just keep on concentrating the feed solution until we reach crystallization of for example, the minerals or the other valuable resources that we have in the water. So here you can see a comparison between membrane distillation or membrane crystallization versus reverse osmosis. And this was my co-supervisor at when I did my PhD at the University of Calabria, an institute on membrane technology, who have made this figure. And here you can see like the flux on the y-axis, and then versus the concentration. And the purple line here is for reverse osmosis. So what you can see is, and I have to say this is made for like seawater or brine solution. So what you can see is that when we increase the concentration with reverse osmosis, the flux or the performance of the membrane is decreasing quite drastically, whereas with membrane distillation, it decreases a little bit depending on the concentration, but not much. The one that, or how to say, like the temperature has a strong influence on the flux. So higher the temperature is, the higher is the flux or the performance. But this figure really shows where membrane distillation or membrane crystallization can be used. But this is for the complex solutions where we also have high concentrations, high osmotic pressures. In those kind of solutions, membrane distillation is working very well. And here you can see some of the minerals that we have recovered from different feed streams. So of course it's not directly related to biorefineries, this work, but it's just to say that if we have some resources that we would like to recover, that could be a potential possibility. And here you can also see a figure of the crystallization process. And normally you can obtain crystallization either by decreasing the temperature, so by cooling. So this is the solubility curve. So we have to be about the solubility in order to have precipitation. So we can either cool the solution, so we go into the metastable zone or above, or we can do evaporation. So in membrane distillation, membrane crystallization, we evaporate the solvent in the solution, and that we keep on doing until we reach crystallization. And this process we can actually control in a very nice way, because we would like to be in the metastable zone where we can control the crystallization. If we are above this zone up here, then we have spontaneous nucleation, which we need as a start, but we will also see many small crystals. So if we are in this zone, we can control the crystallization process in a very nice way. And that's also the reason why we can control this in membrane distillation, membrane crystallization, is that every pore in the membrane is making the evaporation of the solvent. So we have many pores, and so we have a very controlled supersaturation gradient across the membrane module. So what we actually have is that we have nucleation within the membrane module, but actually the crystal growth in the feed tank. So this is something that has actually been separated from each other, which is also a very nice feature. And here you can see it's for lithium chloride, but it can be transferred to other components or other compounds. But this is where you see that we change the operative conditions of the setup. So, for example, we change the flow rate and the temperature. And if we use one setting, we have this kind of structure, the elongated structure. And if we change it to some other, we have this more cubic structure. So we are actually able to control the structure. We are also able to control the size in a better way, and thereby also the crystal size distribution. And then we can also see that it's easier for us to have no or low incorporation of impurities, because this process is also relatively slow compared to conventional crystallizers. And here is just some examples that I want to highlight here today of what we have used membrane distillation for. One is for wastewater treatment, for municipal wastewater treatment, where we would like to recover phosphorus from this wastewater, where we first have some biological wastewater treatment, and then we dewater the sludge, and the liquid phase goes into a phosphorus recovery tank, and another part, the sludge, goes into the digester for biogas production, and then it's afterwards dewatered, and then again the reject water goes into this phosphorus recovery tank. And today, normally what is done is with fluidized bed reactors, at least in Denmark, where we add magnesium and we adjust the pH. And then we recover phosphorus as chloride. And that is today a challenge, because phosphorus is like a scarce resource, so we would like to recover it, but it also precipitates in equipment and pipelines. So it's something that we would like to be able to control in a good way. And here we looked into if membranes could improve the phosphorus recovery from wastewater. And here are some results. They are a little bit old results, but they're very useful. Here we tested membrane distillation on the reject water from the digester from a wastewater treatment plant here in Aalborg. So it's real wastewater streams, and here you can see that the flux using different temperatures are quite stable, even at very high recovery factors. And the temperature as well was very stable, which is the driving force. So the membrane distillation runs very smoothly. And here you can see like a figure of what is it that we actually can recover. So the difference between these two lines or these two curves is the amount of phosphorus we actually recover. And this is what we do with conventional recovery with fluidized bed reactors, is around 40%. But if we use membrane crystallization without any control of pH, any control, we only do the membrane distillation, membrane crystallization, we are able to increase this to 60%. So this is something that could also be optimized in a better way. And then we also see some different structures of the phosphorus, as you can see here. And that is something that we believe that the structures here are also important for how the crystals are aggregating. And that is important again for what we can use the product for in the end. Another part of this, and I know INTEC and Bettina also worked on this with the ammonia recovery using membrane distillation. And this we also did in the same study, so we simultaneously recover phosphorus while we also recover ammonia. Because ammonia is volatile, so that will, together with the water, go through the membrane into the pyramid stream, and that you can see here. That is just related to the conductivity as we measured here, so that there is an increase in the pyramid conductivity, but that is due to the ammonia transport into the pyramid stream. So membrane distillation together with membrane crystallization can actually be a solution for simultaneously recover phosphorus products and ammonia if we do it for this kind of wastewater stream. So I think that is very interesting. We have shown also in some other studies that again that we can, depending on the temperatures that we are using, we can increase or decrease the flux and also control the ratio between ammonia to water. So it's something that is controllable in this process as well. And then I will also just, again, it's not directly connected to biorefineries, but I'm coordinating a project, a EU project where we do battery recycling. And when you do battery recycling, you also use acids. And this is where biorefineries really plays a very important role in future, is to make the leaching solution for battery recycling or other electronic scrap recycling. So here the challenge is, of course, that we would like to use more batteries in Europe, but we actually only recycle very small amounts of this of the batteries, and that can be car batteries, from solar panels, from computers, and so on. And we see that we'll probably have an increase, or we will have an increase of what we need to recycle. So this project is looking into that. And of course, there's a long value chain of battery recycling. So there is like dismantling, deactivation, sorting, and characterization we're also looking into. But where I would like to focus today is on the recycling and regeneration. And here you can see that we have a bio-leaching step. So we produce biogenic acids from biomass through the bio-leaching of the what is called black mass in battery recycling. So like the solid waste, and we do the bio-leaching, and then we can concentrate or regenerate the acids, and we can also recover the metals from the stream. And here we are using, again, membrane distillation and membrane crystallization. And then we compare the bio-leaching with the conventional sulfuric acid leaching. So that's also a very nice concept to see how this is correlated. And here you can just see some of the results we have on the acid concentration. So this is the short-term experiments where it's around 2 hours, if I remember correctly, where we have both tested direct contact membrane distillation. That is where we have both liquid streams on both sides of the membranes, and then vacuum membrane distillation, where we have vacuum on the pyramid side. And here you can see that we actually are able to treat quite high, and this is with conventional sulfuric acid, I have to say, for these figures. But we can treat different concentration of sulfuric acid and obtain very high rejections of of the sulfuric acid. So it's about 99%. So very high rejections, and that is the same both for DCMD and VMD. In VMD, we get slightly higher fluxes, as we also would expect. And we also did it for long-term operations where we could concentrate the acid more than 2 times with different concentrations in the beginning. So this is like both done for 1.1 molar and 1.5 molar. So it's also a quite high concentration for the leaching. And again, we obtain very high rejection but stable performance. And that we then compare to the biogenic acid that we produce. So one partner in this project is producing the biogenic acid, but because the biogenic acid is not possible to produce that in very high concentration. So what we do in this project is to see if we can concentrate the biogenic acid. And the results you can see here with membrane distillation. Here we also get relatively high or stable fluxes. So we can see that membrane distillation can be used for the concentration of acids. And then we also showed that this solution can be used for leaching out of the metals in the solution. And then actually at the same time we can also use membrane distillation, membrane crystallization for the recovery of the metals and minerals. Where we are right now in the project is that it's just a mix of all kind of different metals. But if you're interested, we can show you more on this. But we have not been able to selectively recover any pure or purified metals. And then the idea is that after we recover these metals, then the acids can potentially be reused as well. So we both concentrate the acids same time as we recover the metals, and then we will recycle these acids. So this is a process where the biorefinery or the biogenic acid production really can play a huge role in future recycling industries, not only for batteries, but also for other solid waste. So I think that is something that is of huge importance. And here membrane distillation can play a role. So yeah, this is the consortium that we have for Beyond Brick. Yeah, and then just some very short final thoughts of this presentation, that membrane distillation, that you can also think of on your own work and your own results and your own streams, that it can be used for concentration of many different streams, and it can also, if we use it as membrane crystallization, it can recover many different valuable resources within the streams. And then I think also one important part is that there is also like these synergetic effects that we recover the water or the other solvent in the solution. We can use waste heat or alternative energy sources, and then we recover the resources. And these things should be considered together, and that is where membrane distillation is a very nice process. And yeah, this is just our group here in Aalborg working on membrane distillation, and then some of the project that we are working in, and these are the European projects, and then we also have some national projects. So I think actually this was all for my presentation, but of course if there's any questions I would be happy to answer them. I know it was not so much into the biorefinery, but it was more to give an overview of what membrane distillation, membrane crystallization potentially could be. And of course I'm always open to collaborate. Thank you.
Many thanks, Chesna. This was a really great overview, and I think it highlights so much the importance how MD can really help in resource recovery, which is a highly important topic currently. We do have one question in the chat, as I see, from Christine. Christian or Christine? Feel free to ask your question.
Yes, thank you for the nice presentation. I have to say, I'm also a fan of MD, and so we are also doing a lot of MD research on several applications. But we have, however, problems with selling it to industry because the amount of MD modules on a larger scale is limited and is decreasing, unfortunately. And I'm wondering how you are dealing with this, because lab scale results is one thing, pilot scales is also still feasible, but the next step is limiting us.
Yeah, and I think actually that is a huge problem in MD research. That is really that we do not have the available modules from companies. We use mainly hollow fibers or capillary fibers. And we can buy modules, for example, from Man and Hummel. But of course, actually, what we do not know is when we use the small modules and how it goes into bigger scale. That is actually something that we are testing now within the Cornerstone project, where IEA Intec is also partner in this. But it is a big problem, and that we don't have available modules. So right now we are using fibers that are made for microfiltration.
Okay, so you're not really using the MD modules like from, we had the ones from Aquastill, or you have the RN Solution. No, you're going completely different systems. Okay, that's interesting.
We have tested also the modules from different partners, and I think that is also, they're working good, but actually, since I studied or did my PhD in Italy, we have used these fibers, and I think I always come back to these fibers to be honest, because there's also something in the packing density. So actually, we can also, so Man and Hummel, they assemble into the modules, but you can also buy the similar fibers in as loose fibers, and then we can. I think what we're able to do now is still very small scale, but 0.6 square meters to 1 square meter in one module. So we're also using those, but of course that is ourselves who's using that. And something that we also consider when you have MD modules, that is that how should they be designed? So when we use the commercial modules not meant for MD, we do a lot of simulation and modeling of the length of the membranes, the packing density, and so on. So I think that is the difficult part, is because that we don't have MD modules. So I agree.
Yeah. Yes. There is a second question in the chat by Cecilia, whether you have looked at the recovery of metals from seawater as well.
I'm really happy for that question. So that is actually our main, maybe what we are working mainly on. It's from reverse osmosis, Brian, so not directly from seawater, but when you have used reverse osmosis to produce drinking water from seawater, we use the brine from there. And here we can start to selectively recover, for example, sodium chloride from magnesium sulfate, but we would also really like to push it further. So we focus also a lot on lithium recovery and how to do that. But it's a challenge, but it's something that we are looking quite into.
Many thanks, Chesna. I would still have a lot of questions and discussion points where we could go on, but I think we have to postpone this looking at the time.
Oh, thank you.
But many thanks, and we know Chesna is just an email away to discuss. Mauricio, did you was a hand raised. Okay. Yeah, but given the timing, I think we will move on for today. I'm now in a little bit the awkward situation of having to announce myself as next speaker, because as Chesna said, we in our group, we are also focusing a lot on ammonia recovery, and I'm happy that I can give you some insights. Just bringing this into the presentation mode, and I hope it works fine for everyone, but I can give you some insights in the next 15 minutes on our results over the past years. So how we evaluate operating parameters in pilot scale membrane distillation for ammonia recovery, where we recently focus most on biogas digestate. As said, we work on ammonia separation via membrane distillation for a very long time, and this on the one hand can be applied for centric water of wastewater treatment plants, for optimizing biogas plants, but of course also for biorefineries or any industry with highly organic or ammonium polluted waters. How does the process work? Thanks to Chesna, I don't have to explain the concept of membrane distillation, but really can focus on how this is done for ammonia separation. So as we've seen, we use a hydrophobic membrane in membrane distillation, and this means only ammonia in free form passes the membrane, because vapor pressure difference and vapor pressure difference between the feed and the permeate is our driving force. Now we can do that in several membrane distillation configuration. The ones we are looking at most is direct contact membrane distillation, where we have a liquid on both sides of the membrane. And now typically the feed can be, for example, a digestate, a centric water, an ammonium loaded wastewater stream. And on the permeate side, we basically collect the ammonia in an acid solution, for example, in sulfuric acid, where the ammonium sulfate salts are formed. And by this, we basically, because there we have zero vapor pressure on the permeate side, so we have a constant driving force from the feed side to the permeate side. One aspect of this is that in standard membrane distillation configuration, we usually also have a temperature difference between the feed and the permeate stream. However, once we have a temperature difference, not only ammonia will see a vapor pressure difference, but also water will see a driving force induced by temperature. And in our processes, we try to also use this permeate solution, this ammonium sulfate solution further on, and here higher concentrations are beneficial. So what we would like to do is transfer ammonia, but limit the transfer of water. And in order to do that, we work isothermally. So we have the same temperature on the feed and the permeate side, and we only use the concentration of the feed to induce the vapor pressure for our ammonia. And the other process we are also looking at, but today I will less focus on that one, is vacuum membrane distillation. Here we can collect ammonia at the permeate in gaseous form and use it as fuel or chemical in the gaseous pathway. And of course, also here, the question is always, is it only ammonia? Water will be, in this case, always transferred with the ammonia because of the pressure difference. Water will also see a driving force. We started working on this at the beginning, let's say, 6-7 years ago already. And our first projects were focused on ammonia removal from centrate water. And we operated there a pilot plant at a local wastewater treatment plant close to our research institute in semi-batch operation. We treated about 1 cubic meter of centrate water per day. And we could show that we have a very high removal of ammonia, so over 95%. We could really go down to very low ammonia concentrations in our effluent, so in the feed that left our system. So we could really have here a very high reduction of the ammonium load of the centrate water. What was most important for us in this first, let's say, longer term evaluation in pilot scale mode was that we had a stable and robust operation. And we reached an ammonia sulfate concentration at the permeate of around 25 grams per liter. So as said, we could, with this isothermal operation, really increase the permeate concentration. However, we have also seen that we cannot reduce the water transfer to a minimum because of the different conductivities in feed and permeate side. We will always have some water transfer linked to the osmotic pressures. This is an insight of the system we operate. So this is our container. It's currently at the back of our lab site at our institute. And here we can operate modules between 2 and even 14 square meters. We did already. And our feed tank has typically 100 liters. So this is typically one feed patch we operate with. Now, this was the early work with centered water, and since several years now, we are focusing more on the treatment of digestate. So in this graph, you see in the middle of the graph, I hope you see my mouse, the biogas plant. Now, in any biogas plant, digestate is produced, and digestate is usually now used on the agricultural field. However, there's in many cases, either logistics problems, limits on how much can be actually put on the fields. So ideas are being sought on how we could actually have here more value from the digestate. And one idea is to do a solid liquid separation and treat the liquid with, again, isothermal membrane distillation to produce a nitrogen liquid fertilizer. I will first focus on this part of the solution via membrane distillation. There's another one where we can apply membrane distillation connected to biogas. Well, I'll come to that in a minute. So let's first focus really on digestate treatment. So currently we have a lot of biogas plants in Europe. As we know, the liquid digestate actually has a high nutritional value. However, the question is how we can really make this best use, and can we produce an ammonium sulfate or let's say an ammonium fertilizer. So far it's ammonium sulfate, but maybe we can even use 2 other acids. Just that this works. Yes. We started this, studying the digestate from an Austrian brewery where they do a spent grain monofermentation biogas plant, and we used that digestate first at low temperatures. You see above here the different, or some of our MD experiments that we performed, where we also published the data. And here you can see that usually we did 24-hour runs, so always 100 liters of digestate were treated over 24 hours in the beginning, and then we prolonged the experiments to 64 hours or even 168 hours, so running 7 days through, where of course the feed was then exchanged several times. These results have been published together with our earlier colleague and still close friend, Elena Guyen. She's currently working in Catalonia at the Politecnico there, together with José Luis Cortina. And in our publication, we compared then our results with the membrane distillation with results they performed also on membrane contactors. However, today I will focus really on the membrane distillation results that we achieved. What is important to note is that we adjusted in this work in the early days, let's say, the pH of the feed solution. So this was around 9.2 to 9.4. And this was adjusted by an addition of sodium hydroxide. When we look at the flux that we could reach, we can see that actually, first of all, this was nicely reproducible. During our experiment duration, we had average fluxes ranging from 3 to 5 grams per square meter an hour. And of course, this reduces after a certain time. So especially our very long runs, for example, here, where we went to a very, as you can see in this graph, this run number 3 here, we really went down to very high, we went down to very low feed concentrations or very high removal of ammonium. And of course, because we then have a very low feed concentration, the driving force drops, and so does the flux. It is, however, interesting that in this research, we didn't really see fouling visible. Yeah, flux over time was well linked to the feed concentration. We know we have vapor pressure as driving force, so of course the feed concentration is let's say driving force in our system, and we can see that here, for example, in the graph on the left side, where we see the reduction of flux, of course, over time. But when we evaluate it, and here Elena did a very interesting work on evaluating all of our results based on the free ammonia concentration, actually, we can see that we have here a nice linear relationship. However, when we would have fouling, like in other systems, for example, with this membrane contactor, this would drop suddenly significant because flux would go down, but not in relation to the feed concentration, but in relation to fouling. And this is in line with earlier results. We also did some EDX analysis after a very long-term run of our modules, and we always find a nitrogen-rich layer. However, this is not negatively affecting flux. In this work with the brewery digestate, we processed in total 2.1 cubic meters of digestate. We produced almost 300 liters of permeate, and we could were interested in what final permeate concentration do we gain. And here you can see that we gained around 14 ammonium nitrogen grams per liter in our in the permeate. So we could, let's say, concentrate from the starting feed concentration to the final permeate concentration. We could reach a concentration factor of over 4. However, when you look at the volumes, let's say we clearly see we still transfer also water, and this is also an analysis we did here. So there is a certain water transfer that we still have in these systems. However, there were 2 challenges that we still saw. Even though we had very nice results, 2 challenges we saw. On the one hand, this can be further increased fluxes. And on the other hand, can we reduce the amount of chemicals that we need for the pH adjustment? Now, then we went into a study where we evaluated higher temperatures, so still on isothermally, but we increased the temperature now on both sides, feed and permeate at the same time. And in these graphs, you can nicely see that we did here 24-hour runs of our 100-liter feed batch with 2.3 square meters of membrane size. And you can see nicely that the higher we go with temperature, the more we can increase the flux. And what we also know, of course, the longer we operate, at some point flux drops significantly because of lower feed concentration. So if we just look at the data where the feed concentration stays above 0.25 milligrams per liter, we actually see that here we have really nice values, almost 20 grams of ammonia flux per square meter and hour. Now we actually could show that digestate treatment works very well. This is of course related to the fact that this is a fermented substrate. It comes from an organic plant, and it's a biogas plant. We have a hydrophobic membrane, so usually organics really wet our hydrophobic membrane. But in this case, these organics have been fermented. And because of that, actually we can reach really these very robust and stable conditions. Now, another option that could be very interesting is linking the membrane distillation process, once it works so well, to actually reducing the ammonia load in the fermenter itself. So here we have, of course, a mix of fermented and unfermented substrate, but this is the concept that we are currently following. And the results I'm showing you now are really in progress results. So this is the concept. Free ammonia leads to inhibition of microorganisms in the fermenter. It reduces the biogas yield, and the idea is to remove ammonia, especially the free ammonia, from the fermenter substrate in order to increase the biogas yield. What we are currently performing is statistical optimization. First of all, again, looking at the different temperatures. What we are doing in this case is that we are not adjusting any pHs. Yeah, so we don't add any chemicals. We are really working at the pH of the digestate as we receive it. However, for this study, what we are interested in is to find out what is the influence of the different feed concentrations, because then we could give biogas plants, let's say, a design strategy depending on their incoming feed and the amount of nitrogen in the incoming feed. How should they tune the process in order to limit or come to a certain ammonia concentration the biogas plant can still withstand? Yeah, and these are the latest results. So what we've seen in this case, our digestate has a concentration of 4 grams per liter, for example. What we've evaluated here is the the ammonium reduction at different temperatures over time. And when we now evaluate the fluxes at the different concentrations and different temperatures, we can clearly see that higher concentrations lead to higher fluxes, and of course higher temperatures do as well. We have some, let's say, question marks still in our current results, but this is also because we get the real feed from a real biogas plant, and here we can have pH fluctuations. And as we know, pH will influence our results. Yeah, what we can do based on this very preliminary data that we are currently gained is already, let's say, estimating how big would membrane or membrane distillation plant need to be to reduce the ammonia concentration in the fermenter substrate, for example, for a biomethane plant of 260 cubic meters per hour. Yeah, and in this case, we did a very preliminary estimate. However, this membrane area will strongly depend on the steady state pH of the digestate, but we can already see that this process is actually a very interesting one once we don't need any chemicals for it. Yeah, with this, was now running a little bit through in order to catch up time. I already come to my conclusions. We applied DCMD modules a lot over the past years as membrane contactors in isothermal feed and permeate operating conditions. And we could see that this has very high potential for ammonium nitrogen recovery from liquid streams. An increase of process temperature of the isothermal conditions can lead to significantly flux increase, and it can allow that we work with digestate without pH adjustment. So we don't need any chemicals for the feed adjustment. We mainly work with PTFE membranes. We get our modules via a German supplier from Morocco, India, which is as PTFE membranes. They have been proven very stable, and we don't see any ammonia flux reduction really over long-term operations. Of course, only in relation to feed concentration reduction. And the results I didn't show you, but we also could see that only pre-sedimentation was necessary as pre-treatment, and we don't need any other further pre-treatment step. As an outlook, what we are currently trying to do is proving the potential to apply the concept to biogas optimization and apply really our modules to real fermenter substrates. And we have several side research themes in accordance to this. One is that we also, instead of ammonia removal, concentrate digestates for fertilizer via membrane conductors. We also already tried out electrobeam treated polyethylene hollow fibers as alternatives to PTFE. And a current study that will start very soon is that we try out how we could possibly apply organic acids at the permeate side instead of sulfuric acid. Yeah, with this, I would really like to thank a lot the colleagues who are very active in the lab and at the container, Christian, Philip, Mauricio, Pedro, and Guilherme in the last years. Elena, Miguel, and Jose Luis Cortina for the nice publication we could reach last year, and all the project teams of the related projects, and of course our funding agency and financing institutions. And yeah, if there's any questions, I'm happy to answer them.
Thank you, Bettina. I will take over the moderation of the questions. So in terms there are some questions from the audience, please feel free and ask Bettina anything.
Either I was very clear or very fast, but once we are late in time.
There are no questions yet. You can anyway reach out anytime to us. Feel free to contact Bettina or me related to the presentations we had today. I will most probably like to skip the coffee break which was planned, and we will directly go into the last PhD pitch session. Since we had some delay earlier, I would now kindly ask Joy Madhumita to present his PhD topic.
I'm Joy Madhumita. I'm a PhD research associate. I'm working in Water Institute in Karunya Institute of Technology Sciences, Coimbatore, Tamil Nadu, India. I'm under the supervision of the Dr. Jagadambal. She's professor of Water Institute, and she's DARS Research Ambassador of India. I'm going to present in the topic analyzing the fabrication and characterization of organic, inorganic, and clay nanocomposite membranes, PVA, PVDF, and PES. And this is a very huge topic. I try to cut short at present. The contents. The introduction and background of this, the nanocomposite membrane I'm using, it is the nanoparticle is embedded into the polymer matrix to reduce the pore size. It is of less than 2 nanometer and improve the selectivity, enhancing the properties like hydrophilicity, mechanical strength, and anti-fouling for application in water treatment, gas separation, and fuel cells, biorefineries, etc. Methodology. It involves the fabricating hydrophilic PVA, hydrophobic PVDF, moderately hydrophilic PES materials, and followed by characterization test, water uptake, porosity, FSM, EDAX, XRD, FTIR, contact angle, permeability, anti-fouling, zeta potential, to analyze their properties, leading to the results and discussions. And this is the materials and methods used to analyze. And this polymers, PVA, PVDF, and PES, polymers are selected based on their wettability, affinity towards the water. And the organic nanomaterials taken by the, it is organic, I've taken the carbon based as powder activated carbon and carbon nanofiber in the aim of increasing the porosity. And inorganic material, I take the zeolite and clays. We know the clays having the silicon and aluminum group, and this zeolite also having this composition. It composed of silicon, aluminum, and oxygen. And this clay, I take the 3 type of clay: MMT, kaolin, nano clay. It is based upon the sandwich layers of tetrahedral and octahedral. And the MMT is it is alternatively tetrahedral, octahedral. Kaolin is tetrahedral, octahedral. It is a single 1:1 ratio, and nano is 3:1. 3 part of and 1 part of octahedral group. And this design of this experiment, to choose the percentage of polymers and nanomaterials used, we can run the possibility through the design expert software. STAT is intact. From this, we can optimize the preparations. I taken the filler concentration, polymer concentration based upon the fluxus response factor. And this synthesis of membranes, there are many membrane synthesis methods, layer by layer assembly, electrospinning, phase inversion, sol gel method, etc. And these also methods. And the PVDF and PES, the hydrophobic fabrication methods, it is prepared by the immersion precipitation, phase inversion method. The percentage this percentage of this polymer was selected based on the literatures after more trials. And PVA membrane fabrication, it is blended with PVA plus with glutaraldehyde for making the hydrophilic PVA to hydrophobic. Because my working environment is water, and by solution casting and cross-linking method, PVA membrane is fabricated dyeing in hot air oven after casting, and also by coagulation bath. It is an immersion precipitation principle. It is used the salt, sodium sulfate and sodium hydroxide salt. And the parameters to be analyzed: pore size, it is analyzed by FSM, EDAX, and thickness by microgauge, charge by zeta potential, functional group FTIR, flux and anti-fouling, data infiltration, crystalline arrangement XRD, physical characterization. This porosity, water uptake, these are characterized using it can be tested in our laboratories. The water uptake using this wet and dry efficiency formula, and porosity, it is using the wet and dry with density and thickness formula. And mean pore radius is by Guriot-Alford-Ferry equation. From the graph, we found porosity is directly proportional to the water uptake capacity. When we add nanoparticles, the pore size got increased and porosity also got increased. The results and discussion of the PVA and PVDF and the clay nano composite membranes. PVA membrane is very thin and high water uptake, the less porosity with small pore size, and PVDF membrane are having more porosity. Clay added to membranes regulate the water uptake, and organic particles increases the water uptake than the inorganic particles. This PVDF, it's M analysis. This PVDF having a more uniform pore size, a pore structure, and is a spongy layer. When we add an activated carbon, it became heterogeneous arrangement. And this PVA FSM, it is less visible pores, densely packed and smooth than the coagulation induced in the heterogeneous. This PES, it is homogeneous pores. When we add a nanoparticle, it increases the internal voids and channels buildup is observed. And this EDAX, energy dispersed spectroscopy, all the polymers having the carbon, oxygen and nitrogen group common, and PVDF has the fluorides and chlorides, halogen groups, making the polymer more electronegative. And FTIR, these peaks confirms the presence of the sulfonic groups, amine aromatic ketone groups in this polymer. I have taken only for the polysulfone membrane polymers and their nanocomposites. Contact the contact angle, it is taken for the PES membrane, that is between 70 to 80 degree. This is moderately hydrophilic because it is less than 90 degree. And zeta potential of the sulfone and the particles of nanoparticles are only analyzed. I analyzed here. This negativity shows that it is negatively surface charge. This shows the stability, indicates a good surface charge stability in this particles. And the XRD we can analyze by Bragg's equations and plotted. The crystallinity and peak shift reflects the incorporating additives into the polymer matrix, affecting the material structural properties. The rejection mechanism in the polymers are based on the size exclusions and the hydrophobic interaction, polarization effect on the surface, charge of the membrane. This permeation test I have done using this dead-end filtration, where the fed solution is allowed to pass perpendicular to the polymer. And the color removal efficiency, for that I used two types of FET solution. First is a pure water, is the distilled water, and the dye water. My work is based on the dye removal and the flux study. The flux is the volume passed to the area in the given time, and in presence of a constant pressure. I take an optimum pressure. First I take with a minimum pressure of 2 bar, a maximum it having a 14 bar setup, and in 10 minutes I collected the readings, and I observed that the adding the nanomaterials increases the flux in both. If it in the dyes, if in a control polysulfone, controls a pure polysulfone, the fouling is occurs and the will go the removal efficiency and fluxes for reducing. But in the nanocomposite membranes, the flux is became a stable. Fouling and anti-fouling studies. This flux recovery is a measure of fouling, and total fouling ratio is measure of anti-fouling performance. And this is the fouling of the membrane, and and after we can backwash, this membrane can be reusable, and the efficiency also will be good. And in this also we will observe that nanocomposite membrane shows a good performance than the control membranes. And results improved the nanocomposite membrane improved the flexibility and hydrophilicity. Inorganic nanocomposites are enhanced flux and anti-fouling properties. The clay nanocomposites improves barrier properties and selectivity. And this fillers of maximum performance. And if excess fillers is added, will lead to agglomeration and performance decline. The PVA membrane is high hydrophilicity and low stability. PVDF is chemically resistant and hydrophobic, and PES is thermally stable and fouling tendency. Nanocomposites improved overall performance and dispersion challenges. Conclusion, it increased flux ejections and fouling resistant. And again in future direction, I used to use it for the green synthesis to make the membranes, and hybrid nanofillers are going to up and make it to be a scale up with for industrial applications. References attached. Thank you.
Okay, thank you, Mr. Mohamita, for the presentation and also for the spontaneous change in the program. We will directly continue with Ali Zain Hamid from Lund University and University of Twente.
Okay, so I am Ali Zain Hamid. So I will present my recent work, with the title Electrostatic Regulation of Fouling in Ultrafiltration of Protein Stabilized Oil Water Emulsions. And this work is done with the supervision of Antoine Kamperman, Franz Lipinski, and Wiebe de Vos. I'm also part of MEMFAST project, in which we are developing membrane technologies for sustainable biorefineries. So biorefinery industries have these biomass feedstocks, for example, these oilseed processing microalgae biomass or protein streams. They come up with both the oil and the proteins. Now these proteins, they are amphiphilic in nature. They have both hydrophobic and hydrophilic groups. And they absorb at the oil-water interface when we are trying to extract the oil in the wet processes, and they form these stable oil and water emulsions. If we want to separate these oily emulsions using membrane technology, then they leads to membrane fouling, and it has a lot of other problems. For example, high process cost. It reduces the oil recovery, and then finally, if these oily streams are dumped into the waste, it leads to oily wastewater streams, which have there a lot of bio-based implications. So this is field conditioning. Basically, this is the framework of this work. So in this case, we adjust the chemical environment of the feed to achieve specific properties inside the emulsions. For example, we change the feed condition using pH and salinity. When we change the pH and salinity, it changes the protein interfacial properties. For example, their charge state, how they're gonna conform, and also how they're gonna absorb at the interface. Based on their interfacial properties, we are dictating how their droplets gonna interact inside the emulsions. Either they're gonna repel each other, or they're gonna coalesce or aggregate inside the emulsions. And based on the droplet interaction, we will decide the emulsion structures. Either we're going to have dispersed droplets inside the emulsions, or we have aggregated clusters inside the emulsions. And finally, these emulsion structures will determine the membrane fouling behavior. For example, if we have dispersed droplets inside the emulsions, we have open K clear, and it means to higher flux. And we have aggregated cluster inside the emulsions, we have dense K clear and basically flux decline. So here we have the droplet interaction with respect to the pH. So what pH does, pH basically changes the charge and interfacial properties of the proteins. So here we have 100 ppm rapeseed oil emulsion with beta-lactoglobulin protein as the stabilizer. So at pH 2, we have the proteins are nicely positively charged. So they have this significant repulsion between the droplets, so we can see nice individual droplets. At pH 7 and 10, the proteins achieve a strong negative charge, and hence we again have repulsion between the droplets, and we can see individual droplets. But at pH 2.6, which is the isoelectric point of the proteins, we can see that the proteins agglomerated at this point. And now they are agglomerated. It means that they are not uniformly dispersed, but in this case, still they are maintaining their individual boundaries, which shows that the protein stabilized emulsions behave more like Pickering emulsions instead of emulsions which are formed by chemical surfactants in other industries. Moving forward with the droplet interaction with ionic strength. So what ionic strength does, or added salt concentration does, it basically shields the charge between the proteins, of the proteins. So here again we have these rapeseed oil emulsions. So initially we have this beta-lactoglobulin protein. At 1 millimolar salt concentration, we have nice individual droplets. But as we move towards higher concentration of salt, we can see that these agglomerates are getting formed, and they are loose flocks where droplets are still maintaining their individual boundaries, and the size of these flocks are just getting bigger. In the case of another protein, which is ovalbumin, in this case we can again see that at higher salt concentration, we are observing these formation of these flocks. But in this case, the individual droplets are deforming their shapes. So we have denser flocks with droplet deformation, which indicates that the interfacial elasticity is getting decreasing. So at 100 millimolar salt concentration, again we have larger size flocks in this protein as well. So based on a lot of experiments, I have summarized 3 interaction regimes for my emulsion droplets. First is the repulsive regime. In this case, the charge on the membrane and the droplet is identical, and in this case, there is significant repulsion between droplets, but there is also repulsion between the droplets and the membrane itself. And it happens usually at moderate to higher pH values. In this case, because of this repulsion, we have a lot of permeate that passes through the membrane, and we have open and more reversible K clear. Then we have this charge neutralization regime. In this case, the droplets agglomerate inside the emulsion, but they also agglomerate on the surface of the membrane itself. So because of this agglomeration, we have compacted K clear, and it leads to very less flux, as you can see here. Finally, we have charge neutralization regime. In this case, the added salt particles are basically shielding the charges on the protein as well as in the membrane. So the droplets are now closer, but they're also getting more strongly attracted toward the membrane. It means here we have a denser K clear, but we also have a strongly adhered K clear to the membrane itself. So we again have lower flux. So as a result, a physiochemical framework linking protein interfacial properties to ultrafiltration fouling behavior was developed. pH is controlling protein charge and droplet stability, while the increase in salinity is screening the electrostatic repulsion and promotes aggregation. Finally, electrostatic regulation is recognized as a practical tool to control separation performance in bio-based processes. So I will acknowledge the support of my supervisors in the project, and your questions are appreciated.
Okay, thank you very much for keeping the time and for the interesting presentation. Do we have some questions from the audience? If we do not have any further questions, since we are already a little bit overdue in time, I would kindly ask our next speaker, who is also patiently waiting for finally being able to present, Yongji Liu, will be talking next, and he's from University of Calabria as well.
Yes.
Please.
Can you hear me? Okay. So good afternoon, everyone. I'm Yongji, and today I'm excited to share our work on oligoganacturonide production from pectin by enzyme membrane reactor. So in the field of biorefinery, we often talk about turning waste into value. However, most current processes are highly energy and water intensive. While membranes can help recycle the water and lower the energy use, but their overall efficiency still needs to significant improvement. So my research focuses on developing eco-friendly nanostructured biocatalytic membranes and membrane bioreactors. By combining reactions and separations, we aim to make biorefinery process much more efficient. So my work involves comparing free and immobilized enzyme systems to determine which one is more effective and stable over time. So, however, for today's pitch, we will focus specifically on only free enzyme configurations. So, a case study here, we are looking at pectin-rich biomass. These are common but underused resources such as apple peels and the citrus wastes. So looking at the pectin structures, it consists of several parts, but the main component is the HG part. Which is a chain of the galactonic acid. So our goal is to use enzyme to hydrolyze these long chains into shorter units, especially 2 to 20 units long. We call these oligoganacturonides. And they hold high value for both human and plant health. So in our research, we use indopectinase to random cut these chains to achieve this aim. So while we apply a membrane, it acts as both a separator and a controller of the reactions. And if the enzyme are immobilized on the membrane itself, membrane, it is also a reactor, a separator, and a reaction controller. But today we are comparing only two free enzyme configurations. So first, it is the stir tank reactors followed by the ultrafiltration. The second, it is the enzyme membrane reactors, we call it EMR, where the separation and the reaction happen simultaneously. So these are the two differences. So first, let's look at the STR. We use this step to evaluate pectinase activity at different temperatures. As you can see in this figure, the concentration of the galactonic acid here, it is the concentration of the galactonic cells part of unreacted pectin in the tank. So the slope you can see here, the decline, it means the how fast it is the reaction happens. So our data shows that at 40 degrees, the reaction reaches to the balance in the shortest time, indicating this is the best performance temperature for our pectinase. So next, let's talk about the EMR. When using the EMR, we have to account for the flow rate because we need to recycle the solutions in the tank and use the membrane here. So we tested the effect of flow rates on enzyme activity at 25 with a pressure of 0.3 bar to have some permits, to have some, we want to check if we have any oligoganacturonides. So interestingly, the results here show shows that the flow rate had an negligible effect on enzyme activity. It also follows a very similar trend to what we observed in the STR. So we also tested the option condition of SURF40 in the EMR, and it also showed the same similar trend performance in the STR and EMR. So to conclude, in the STR system, we identified 40 degrees as the ideal temperature for the pectinase activities. And in the EMR system, we found the variations in flow rates do not have significantly impacts on enzyme performance. And most importantly, here is the enzyme activity remained the consistent across both STR and EMR configurations. And thank you for your attention. I'm happy to take questions you may have.
Many thanks, Yongji, for this very interesting talk. And there is maybe one question possible. Anybody? If not, you can anyway reach out to Mr. Liu anytime and ask. Otherwise, I would kindly announce our last speaker of this already very long day. And I thank everyone to still being here and listening to our last talk of Lou Baumes. I hope I pronounced that right, but we will. He will let me know in a minute. Are you ready so far?
Yeah, and the pronunciation is as good as I could hope.
Okay, perfect. Then the floor is yours.
Good evening, everyone. Thank you all for the very nice presentations today. For the nice talk and the nice speeches. So my name is Lou Baume. I am working in Lund University. And my PhD project is inside of the MEMFAST project, and you've already seen some of my colleagues presenting so far. I'm working on the supervision of Professor Lipnitsky that you've heard earlier today. My topic is novel membrane bioreactors for continuous processing of biofuels and biochemicals. When I say biofuels and biochemicals, what I actually mean is bioethanol as well as biobutanol. So to give a little bit of context, bioethanol and biobutanol, we can produce them through bioroutes through first and second generations. However, the first generation of biorefinery tends to be phased out in Europe in order to not compete to not have like chemicals and fuels competing with arable lands. So we focus on second generation biorefineries, which are using lignocellulosic matter, which in my opinion is the most interesting one because they prompt valorization of the waste streams, which can help promoting circular economy. So second generation deals with this lignocellulosic biomass, which has the problem of requiring some pre-treatment in order for the microorganisms to be able to access sugars in order to process to set fermentation. The sugars we're going for are glucose from the cellulose and xylose from the hemicelluloses. And the pretreatment, which can be, for example, hot water pretreatment or steam explosion, tend to leave our compounds in very diluted states. On top of that, the fermentation broth in itself is inherently dilute because live cells require an aqueous environment. A third problem that we have is that the product accumulation can be limited by the cellular tolerance as some of the target metabolites that we want can prove to be cytotoxic in the case of butanol or simply inhibitory to the growth in the case of ethanol. So to summarize, we have low feed concentration, product inhibition. In some cases, we have also low yields. And all these hindrances amount to the largest cost in biorefineries being the downstream processing, the separation process, especially since we're talking about alcohols, which are notoriously problematic to be separated from water. This all makes the process bottleneck. The aim of my project is to use two membrane approaches, namely fluid osmosis and evaporation, to improve the water management in this process to allow the water to be reused, which is already, water management is already a big problem in general. In situ product removal in order to limit the product inhibition, and lowering the energy expenditure in the downstream processing. To frame it more synthetically, I want to optimize the solventogenic fermentation process, integrate the recirculation of draw solution and retentate for fluid osmosis and evaporation, simplifying the downstream processing of the solvents for product isolation and purification, and in the end, to be more industry oriented, our goal is going to have some economical benchmarking. So the continuous, so we want a continuous process. It's set up around submerged membrane bioreactor. It contains a microfiltration ceramic membrane, which allows to draw the fermentation broth from the fermenter while keeping the cells inside, which helps us for once to maintain the cell population, as well as to limit the biofouling on the next steps. Just the implementation of the continuous allowed us to jump from 75% of the ideal ethanol yield to 94% of it, which is already a sign that we're going in the right direction. And the idea is to implement it with a fluid osmosis module as an early downstream process, which would allow which could be followed, for example, by nanofiltration to reuse the nutrients that are going to leave with the ethanol, with the ethanol or the butanol. And lastly, the idea would be to just merge draw solution and feed, and to use an industrial side stream to fuel our fermentation. And when it comes to the integration of the evaporation, it's even more straightforward because we just want to we're just doing like straight up in situ product removal. And yeah, the idea here is going to be mainly to to put all that into practice. And I think after that I'm done with my 5 minutes, and I'm even eating a little bit more. So I'll just thank you for your attention, and I'll welcome any questions.
All good. Thank you very much for this nice insight in your PhD topic and for the excellent presentation. Are there any questions open? Could be also addressed to the last 2 or 3 PhD pitch presentations, since the speakers are still here. Yes, Priyanka has a question. Now you should be able to. Sorry.
Yeah. Thank you. It's very nice presentation, Lou, but it's interesting quite to see the application of the forward osmosis too. I was a bit wondering what you used as a draw solution during your forward osmosis experiment.
Right now, we're just doing, we're just basically trying to prove the process to get everything to work together. But some of the things that have been thought of are, one of the obvious choices would be sugar molasses, mainly from beets, because we don't have that much sugar canes here. And also there was thought about trying to follow the work of a man called Kalafatakis that basically did this, started doing something like this, using crude glycerol from the biodiesel production. It's like a side stream of biodiesel production.
Yeah, actually, the thing is when we always, in case of forward osmosis, is the challenge is to draw solution recovery. So that is always this a challenge. For every process, it comes with a challenge. So that is a thing that I was thinking like. But okay, anyway, thank you.
Pleasure. But yeah, I mean, the whole idea behind it is to try to remove this problem, because the discarding the draw solution is always the difficult part. So if we can discard it in our fermenter, it will solve everything.
Yeah, indeed. Best of luck.
Okay, we are coming to an end of this very long day, and to finish up, I'm very happy that this day went down without a lot of problems, even though we had 2 or 3 speakers who were not able to present due to some issues. However, I think it was a very productive day, and thanks again to all speakers, contributors, and everybody who helped preparing this workshop. I just want to remind everybody that you are all invited contributing to our Membranes in Biorefineries Guideline update. And after this workshop, you will get an email from me with all the information, with the link to the streaming after we cut the video, and the template for your contribution. I would also like to thank my colleagues from TU Vienna especially, and thank Neda and Michael Harasek for the co-organization. And maybe Neda wants to also say a few words.
Thank you very much, Christoph. I would like to thank you, thank all the speakers for the excellent presentations, and all participants for their valuable time and engagement. And also a special thanks to you for your supportive role in scheduling and rescheduling in this very long day, and also to organizers of this webinar for making this event possible. Yeah, that's it from my side. I'm very happy to be a part of this webinar, and I hope to see you again in future events, and all the participants also.
Okay, thank you everybody, and have a nice evening, and see you very soon.